Astronomers have mapped a giant structure made of dark matter. It extends almost 60 million light-years out from a huge galaxy cluster, and is our best glimpse so far of the scaffolding that gives the universe its large-scale structure. In its very early years, the universe was extremely smooth and uniform. There were no stars and no galaxies, and all of the matter was distributed throughout the universe very, very evenly, almost perfectly. But not quite even back then. There were tiny variations in the density from place to place and over time. These tiny fluctuations grew and condensed into a web-like pattern that pervades and gives structure to the universe of today, formed of vast filaments and sheets of dark matter. This structure is known to astronomers as the cosmic web. I like to start with a picture I can hold in my head. I close my eyes and imagine the early universe as a warm, nearly featureless mist, a fog so uniform that any two buckets of space looked almost the same. Almost the same, but not quite. Those tiny, tiny differences, 1 part in 100,000, were real, and gravity is exquisitely patient. Over billions of years, those faint ripples in density amplified like gentle swells, becoming ocean waves, then crashing surf. The mathematics you need to describe the beginning is surprisingly compact. If you take a smooth density field and add tiny, random perturbations, then allow gravity to act while the universe expands, overdense regions grow. Under the hood, the growth rate in our best model, lambda CDM, with cold dark matter and a cosmological constant, is set by simple balances. Gravity tries to pull, cosmic expansion tries to dilute. Write it down and you find that overdensities grow roughly in proportion to what cosmologists call the growth factor, a function of time governed by the contents of the cosmos. You don't need to see the equations to understand the flow. More matter means more clumping, faster expansion means more resistance. Over enough time, those once tiny ripples freeze into a vast, three-dimensional spiderweb of matter we call the cosmic web. I say matter, but most of that web isn't made of the stuff we touch. I remind myself that ordinary matter atoms, electrons, stars, gas me, contributes only about 5% of the energy budget of the universe. Dark matter weighs in at roughly 27%, and dark energy, that gentle but relentless driver of accelerated expansion, supplies the remaining 68%. If you compare only the matter part, dark matter beats the familiar by about 5-1. So when we talk about the cosmic web, we are mostly talking about the invisible. We infer its presence through its pull and through the way it acts as scaffolding, providing the gravitational backbone along which gas cools, galaxies assemble, and clusters grow at the nodes. I picture the luminous bits galaxies, clusters, arcs of stars, as dew on a spider's silk at dawn, catching the light, but not defining the structure. The silk itself is dark matter. That is why any direct glimpse of the web thrills me. I know there are spectacular simulations where billions of numerical particles stand in for dark matter, and time is marched forward step by step, gravity calculated structures condensing into sheets and filaments and nodes in a visual symphony. But the sky is not a simulation. The sky is data, and data is stubborn. We cannot photograph dark matter. We can, however, watch what it does to light. And here I reach for Einstein, because his theory of general relativity tells me that mass curves, space-time and light follows those curves. The practical upshot is gravitational lensing. Imagine a distant galaxy as a candle, and near a concentration of mass cluster filament halo as a glass lens, and my telescope as an eye. The foreground mass distorts the shapes of those background galaxies in a systematic way. If I map those subtle shears across the field, tiny elongations, coherent alignments, and I collect enough of them with a sharp enough instrument, I can invert the pattern and recover a map of the total mass projected along the line of sight. The key word is total. Lensing doesn't care whether the mass is stars, gas, or dark matter. It just adds. Weak gravitational lensing is delicate work. The signal is small, the universe is messy. The trick is statistics and exquisite imaging. This is where Hubble shines. Its view is above the blur of the atmosphere, so point spread functions are stable, and the tiny smears I am hunting in galaxy images are not swamped by atmospheric turbulence. In this particular case, the team studied a massive, tumultuous galaxy cluster, one of those places where filaments of the web are expected to meet. I think of a confluence of rivers feeding a lake. The cluster known as Max J 717, 5 plus 3,745 is exactly that kind of place, big, still accreting and embedded in a complicated environment. If you're going hunting for a filament, you go where the chances are best. You go to the node. I picture the observation strategy. First, I obtain deep Hubble images across multiple bands to measure shapes and colours of thousands of faint background galaxies. Shapes give me the shear signal. Colours help me estimate which galaxies are behind the cluster and which are in front, because I only want to use those candles whose light has passed through the foreground mass. I then reconstruct a two-dimensional mass map, a kind of shadow of all matter, luminous and dark, integrated along the line of sight. If a filament lies in front of me like a corded rope, that map should show an elongated ridge of mass extending away from the cluster core, and in this case it does. The ridge is not a random alignment of galaxies, it is a coherent strip of lensing signal whose geometry makes sense in the context of a feeding filament. Now comes my favourite twist. A flat map is beautiful, but the universe is not flat. To see flow, to measure infall, I need depth. Depth means distances, and in cosmology distance usually means redshift. Light from a galaxy is stretched by the expansion of the universe. The amount of stretch tells me how far the light has travelled. With ground-based giants like Keck and Subaru, I can take spectra of hundreds of galaxies projected along the filament, measure their redshifts and place them in 3 dimensions. Not just where they appear on the sky, but how far they are along my line of sight. Combine that with measurements of their motions, peculiar velocities relative to the Hubble flow, and I can watch matter stream. I don't literally see it move, I infer it from redshift patterns. But the result is a 3-dimensional reconstruction of the filament's path and the traffic upon it. Here the numbers make me smile because they give me a sense of scale. The filament extends at least 60 million light years in length. 60 million light years is not just a big number, it is a physical span so long that a beam of light racing at 300,000 kilometers per second would need 60 million years to traverse it. In that time on Earth, the lineages of mammals that survived the end Cretaceous extinction diversified into whales and bats. Across that filament, the measured galaxy motions show a preferred direction, streaming along the filament's spine and diving into the cluster's potential well. I see it in my mind like glacial ice flowing into a valley, only here the ice is made of halos and the valley is a space-time well. I want to be careful with what mass means in this context, so I'll walk through it slowly. Lensing gives me projected surface mass density, which I can think of as mass per unit area on the sky. Turning that into a 3-dimensional density requires modelling the geometry and making use of the redshift distribution of sources. When the team converts the signal into a physical density for the filament, they find values consistent with the kind of structures predicted by simulations a few times. The average cosmic matter density stretched over tens of millions of light years with a cross-section that is thicker than a single galaxy halo, but thinner than a sheet. It is not a brick of matter, it is a rope of matter. And the cluster at the end is not a point. It is a turbulent node where multiple ropes tie together. At this point, I can pause and ask a skeptical question. How do I know this isn't some artifact, a coincidence of galaxy alignments, a projection effect where unrelated structures lie along my line of sight? I know because the argument has multiple independent strands. First, the weak lensing shear map reveals an elongated mass over density oriented toward the cluster. Second, spectroscopic redshifts show a physical concentration of galaxies at distances consistent with that mass ridge, not a random sprinkling from a wide range of redshifts. Third, the kinematics, the pattern of velocities lines up with inflow toward the cluster. Fourth, the whole configuration fits within the broader theoretical framework of structure growth from cold dark matter. Each strand has uncertainties, but together they braid into a strong rope. I sometimes repeat that to myself, together they braid, because it captures the way science convinces. I also like to place this in history. The idea that galaxies trace an underlying invisible structure is not new. Observers have seen large-scale clustering superclusters and voids for decades. The cosmic microwave background shows us the primordial seeds. But moving from there must be filaments to here is a specific filament with length, shape, density, and a 3-dimensional path feeding a named cluster is a leap in observational audacity. It marks a moment where our tool-space telescopes with stable optics, multiplex spectrographs on 10-meter class mirrors, refined shape measurement algorithms are finally catching up to our simulations. When I say it's a glimpse of scaffolding, I mean it literally. The web is the load-bearing skeleton upon which the luminous architecture is draped. I know someone will ask what this says about dark matter itself. Does this measurement tell me whether dark matter is truly cold and collisionless, or whether it has some mild self-interaction that could puff up structures? The honest answer is that one filament, even mapped well, is a data point. But it is a crucial kind of data point because the thickness of filaments, the sharpness of their density profiles, and the way matter flows into nodes are all sensitive to the microphysics of dark matter. If dark matter were warm, if its particles had significant velocities early on, small-scale structures would be washed out and filaments would be smoother and broader. If dark matter had strong self-interactions, the contrast could change and cores could become rounder. With enough filaments mapped in 3 dimensions across cosmic time, I could start to separate these possibilities. I could turn a qualitative picture into a quantitative constraint. I cannot resist noting the future, because the future in this domain is dazzling. Hubble's acuity is extraordinary, but its field of view is small, and its sensitivity by today's cutting-edge standards is no longer the ceiling. The James Webb Space Telescope brings infrared sensitivity that turns very faint, very distant background galaxies into usable lensing sources, pushing filament mapping deeper into the past. The Nancy Grace Roman Space Telescope will map weak lensing on enormous areas of sky, with Hubble-like resolution building statistical samples of filaments by the tens of thousands. Euclid, already surveying, complements that with a wide-angle view from space. On the ground, 30-meter class telescopes will place pinpoint redshifts on galaxies threaded along those filaments, adding the 3rd dimension with unprecedented precision. I imagine an atlas of the cosmic web, where every prominent bridge between clusters is charted in 3D, with density, thickness, twist and flow, like a civil engineer's blueprint for the universe. Before I finish, I want to address the invisible but seen paradox one more time, because it carries a quiet philosophical joy. There is no direct photon from a dark matter particle striking my detector. Yet a field of faint galaxies, each a smeared candle at the edge of detectability, carries in their collective distortions the fingerprint of something that does not shine. The math that converts shapes to mass is not magic. Conceptually, it's an inversion problem. If many background shapes are coherently stretched tangentially around a mass concentration, I can work backward to infer the gravitational potential that would produce that pattern. The potential is related to the mass through Poisson's equation. Integrate the relation along the line of sight and you obtain surface density. It sounds forbidding, but the intuition is simple. Mass warps the scene. Measure the warp well enough and you can draw the mass. So here I am, looking at a ribbon of darkness 60 million light years long, traced not by light it emits, but by the way it sculpts the light of others. I see it bend gently toward me, then sweep almost along my line of sight before plunging into the back of the cluster. I see its cargo galaxies caught in the current sliding along its spine toward the gravitational harbour. I see the node swell as it feeds, still growing, still assembling, still burning the fossil fuel of the early universe's ripples into the structures we inhabit. I whisper to myself, still assembling, because it reminds me that formation is not a past tense, it is ongoing. When people ask me what this means for us here now, I say it gives us context. The Milky Way, with all its splendour of starfields and nebulae, is a dewdrop on cosmic silk. Our local group sits on a smaller strand, part of a larger network, whose geometry is imprinted from the earliest times. The fact that we can map a specific filament in 3 dimensions, measure its density and watch matter flow along it, tells me that our theories of structure formation have graduated from broad strokes to fine draftsmanship. It tells me we are learning to read the universe's blueprints, not just admire the facade. And it tells me most of all that the invisible is not inaccessible. With patience, with careful measurement, with a telescope above the air and a spectrograph catching faint lines from galaxies hundreds of millions of light years away, we can take the scaffolding from conjecture to chart. I think that is beautiful. Not because it is grand, though it is grand, but because it is precise. Precision is a kind of love in science. Aim a space telescope, measure 10,000 tiny smears, coax from them a mass map, add redshifts, recover depth, and you have turned absence of light into presence of knowledge. The filament is there, it is long, it is gently curved, it is denser than average by the right amount, it is feeding its cluster, it is the universe showing its bone, and I standing here can say with a straight face that we have begun to survey the skeleton. That is not a metaphor, that is an observation. You're right to catch that. I'm an answer ahead of myself because there's a piece I still want to lay down carefully. The piece that turns a pretty picture of a dark ribbon into a measurement you can weigh in your hands. I mean weigh in the scientific sense, numbers tied to uncertainties, assumptions, stated systematics chased down. When I say we used weak lensing, I'm compacting an entire craft into 2 words. The craft begins with shapes. Galaxy images aren't perfect ovals. They're already a little stretched just by chance. That random out of roundness is big compared to the lensing signal from a filament. So the only way to extract the cosmic warping is to average over many galaxies and to model every non-cosmic thing that also stretches light. The telescope's optics blur and slightly elongate images. The detector's pixels aren't perfectly uniform. The atmosphere would add yet another smear if you observe from the ground, which is why Hubble's stable point spread function is such a gift. In practice, I build a model of the instrument's blurring pattern using stars in the image. Since stars should be point-like, remove that from every galaxy, and then ask across the field whether the residual shapes show a coherent tangential preference around candidate mass ridges. That coherent preference is the shear pattern. Tiny but cumulative, like the way a barely perceptible incline becomes obvious after you've walked a mile. Tiny but telling. Now, shear becomes mass through a geometric lever arm that depends on distances, and this is where the weak in weak lensing is conceptually elegant. In strong lensing, the regime of giant arcs, the deflection is so large that path lengths fold over, and you get multiple images. In weak lensing, no folding, just a small stretch. The mapping between the observed stretch and the mass on the sky depends on a critical surface mass density, and I like to explain that in plain language. The critical surface density is the scale of mass per unit area needed to produce very strong lensing for a given arrangement of source, lens and observer. Its value grows if the source is not far behind the lens, and shrinks if the source is much farther away. In a sentence, the farther the background galaxy is compared to the lens, the more leverage the lens has. When I divide the measured shear by this critical scale and correct for the way shapes scramble when you add up many small distortions, I get an estimate of the surface mass density in the lens plane. Not just the stars, not just the gas, everything with gravity summed along the line of sight, but I don't want to hide the critics in my own head. What about intrinsic alignments, cases where galaxies in the same large-scale tidal field tend to point in similar directions even without lensing that can mimic or dilute the signal? The defense against that is to use color or photometric redshift cuts, so most of my shape sources are truly behind the lens, and to mix in spectroscopic redshifts where I can. What about mass along the line of sight that isn't part of the filament but sits in front or behind and tugs a little on the same candles? That's cosmic noise for lensing. And the way to control it is to go wide in area, to model the contributions statistically and critically in this result, to identify a spine of galaxies that travel together in 3 dimensions, so that what you call a filament is not a mirage but a physical bridge. I repeat to myself, physical bridge, because that is the core upgrade from pretty map to persuasive measurement. Once you believe the bridge is real, the next science question is how dense, how thick, how fast is the flow? The density answer is subtle. A filament isn't a uniform cylinder. Its profile peaks toward the center and blends into the cosmic mean at the edges. Simulations teach me to expect a contrast of a few times the average cosmic matter density within a central radius of order, a megaparsec or 2, that's a few million light years tapering outward. In plain numbers, if you imagine the universe's average matter density as one of healthy filaments, core might be 3 to 10 times that depending on scale and redshift. Converting the lensing map into that profile requires assuming a shape, often a softened, elongated distribution, and letting the data tell you the best fit parameters. The result for this filament sits right where cold dark matter theory would put it. Not a wall, not a whisper, a rope with a measurable waist. Thickness matters because it ties to dark matter's microphysics. If dark matter particles streamed too quickly in the early universe, a warm scenario, the smallest clumps would have been washed out and filaments would be puffier. If they bump into each other, appreciably self-interactions, density contrasts can soften. What we see here, crisp enough to be detected, extended enough to feed a giant cluster without being fat and featureless, leans towards a standard, cold, effectively collisionless picture. I underline leans in my mind. One filament is not a verdict, but it's a high-value data point because it fixes a piece of the web in 3D, which fewer probes can do. And then there's speed. We don't watch galaxies crawl in real time, of course. Their infall velocities are inferred from redshift differences after we subtract the overall expansion. The fact that the velocities align along the filament and point toward the cluster's gravitational well is a dynamic confirmation of the feeding picture. If you want a mental model, think of raindrops on a car's rear window when you're accelerating gently forward. They trace narrow tracks in the direction of flow converging toward the bottom edge. In this cosmic case, the bottom edge is the cluster. The notion that clusters are still growing today by sipping along filaments isn't aesthetic flourish. It's directly supported by the kinematic pattern. At this point, I love to pan out and show how this technique nestles among sister methods. The cosmic microwave background carries the imprint of the original density ripples. Its pattern tells us the initial conditions and the global contents of the universe. Galaxy redshift surveys map where the luminous matter ended up and reveal the cosmic web in light superclusters and voids and long sinuous patterns, but light is biased. It goes where gas can cool and form stars, and where feedback from supernovae and black holes has sculpted it. Thermal Sunyaev-Zeldovich measurements, where hot electrons in clusters and in the intergalactic medium slightly boost the energy of background microwave photons, highlight pressure rather than total mass. X-ray observations catch the densest, hottest gas pockets and have begun to glimpse the warm, hot intergalactic medium along some filament. Fast radio bursts add a different yardstick. The total dispersion of their signals counts free electrons, and so inventories otherwise hidden baryons between us and the source. Each of these is a partial tracer. Weak lensing is special because it goes straight at gravity. It is blind to whether the mass is cold or hot neutral or ionized luminous or dark. It sums everything. That's why I call it the universal ink. I'm also aware of new lensing cousins stepping onto the stage. Lyman alpha forest tomography uses the absorption imprinted on many background galaxy and quasar spectra to reconstruct the 3D distribution of relatively cool intergalactic gas at earlier times. It can reveal the gaseous tendrils that drape the same dark matter skeleton that lensing maps. Cosmic microwave background lensing, measured by Planck and ground-based observatories, and soon in far finer detail, integrates the mass distribution all the way to the surface of last scattering. It paints the web on the largest scales with a single backlight across the entire sky. Galaxy-galaxy lensing, where you stack the tangential shear around many similar galaxies to measure their average dark halos, turns the web's nodes into laboratories. All of these combine into what I think of as a structural ensemble. The 60 million light-year filament pinned down in 3 dimensions is a solo with real virtuosity, but the full symphony is a survey era in which the score becomes a map and the map becomes a catalogue. Let me keep my promise to explain any math in words before I drift into poetry. When I say surface mass density, imagine dividing the sky into squares and asking for each square how much mass sits along the entire line through that square out to the sources you're using. That's a column of mass per unit area. The critical surface density that sets the lensing conversion scale depends on 3 distances from us to the lens, from us to the background source, and from the lens to the source. The larger the last one, the separation between lens and source, the more effective the lens. In simple terms, critical density equals a constant of gravity and light speed times the distance to the source divided by the product of the distance to the lens and the distance from the lens to the source. No symbols needed to catch the idea. Geometry mediates gravity's imprint on shapes. The measured average stretch of galaxy images, the shear, is proportional to the ratio of the actual surface density in that square to the critical density, smoothed by the fact you're projecting 3D into 2D. An inversion algorithm takes the field of tiny stretches and solves for the most likely mass map that produced them. It sounds abstract until you stare at a map with a clear ridge, and you overlay the galaxies whose redshifts place them along a single sinuous path. Then it feels like reading Braille. The raised letters are real. I also want to talk about what 60 million light years means dynamically. The gravitational freefall time, how long matter takes to collapse appreciably under its own gravity, depends on density. In a filament, a few times, the cosmic mean that timescale is on the order of billions of years, which is why these bridges aren't gobbled up instantly. They feed rather than crash. The flow along them is regulated by the depth of the node's potential well and by the expansion of the universe tugging everything out. Dark energy's late time push slows the growth of structure on the biggest scales, but it doesn't switch it off locally where gravity has already dug deep wells. So when I say the cluster is still assembling, I mean that even in a universe whose expansion is accelerating, gravity retains local leverage along these pre-tensed highways. Still assembling. And that echo reminds me that time in cosmology is layered. Some processes freeze out early, others keep humming. Future tools sharpen all of this. With the Roman Space Telescope, shape measurements with Hubble-class resolution will extend across vast swaths of the sky, turning lucky case studies into controlled samples. With Euclid, the wide-field space view is already producing shear maps that cover huge cosmic volumes. Its synergy with ground-based spectroscopy will be to lift those maps into 3 dimensions more routinely. With the next generation of extremely large telescopes, spectroscopic redshifts for fainter, more numerous galaxies will let me thread many more needles through the web. And with JWST, ultra-faint, high redshift sources can act as shape tracers behind structures at earlier cosmic times, pushing the filament census backward to epochs when the skeleton was still knitting. We imagine building a catalogue in which each major cluster lists its inbound roads, the way a city's atlas lists interstates with measured widths, density profiles and infall rates, not soon in human terms, but soon in the terms of an enterprise that measures in light years. Let me close this pass with the human part, which in science is always the part about error bars and humility. The map of this filament is not an oil painting, it's a contour drawing with uncertainties. The densities have ranges. The path in 3 dimensions has error corridors. The galaxy velocities have scatters that we have to model to separate random motions from coherent infall. The team stitched together instruments with different systematics and made choices about how to filter the data and what priors to adopt for the filament's shape. Those choices matter and follow-up will refine them. But I don't need perfection to feel the weight of the conclusion. The mass ridge is there, its arc toward us, and then into the back of the cluster is there, and the stream of galaxies sliding along it is there. The scaffolding is no longer just a metaphor from simulations. It is a measured bridge you can point to and say this one with length and curvature and flow. And I think that's why I drift into a smile when I think of it. Not because the universe is obliged to be legible to us, it isn't, but because we have found ways to read what it refuses to write in ink. We lean on light, on geometry, on statistics on a telescope that stares without blinking, and we reconstruct a structure that is literally dark. We turn absence into inference and inference into a map. We go where filaments should meet. We bring Einstein to the eyepiece and we let thousands of faint galaxies whisper in unison which way space is bent. Whisper in unison, tiny hints aggregated into certainty. And somewhere 60 million light years long, a ribbon of gravity keeps feeding a giant city of galaxies. And we small and luminous have learned to see it. I want to lean into the part we often skip when the pictures are beautiful, the physics of the stuff that rides the scaffolding and the life those environments give to galaxies. A filament is not just a dark rope of gravity, it is also a pipeline for ordinary matter. Hydrogen and helium gas laced with trace metals from earlier generations of stars stream along these lanes, shock heating as they fall and then cooling in patches where density climbs. I picture the gas in phases. Some is hot enough to glow in X-rays near clusters. Some is warm hot millions of degrees, but too tenuous to shine brightly the elusive reservoir we call the warm hot intergalactic medium. Some remains cooler, a kind of intergalactic breeze. Feedback from supernovae and black holes pumps energy back into this medium, stirring it, sometimes pushing gas out small halos and back into the lanes to be recycled later. I tell myself recycled later because it captures how non-linear the flow really is. It isn't a one-way march from void to node, it's a dance with eddies. The cosmic web is a stage for environment to matter. Galaxies that live on thick filaments near clusters tend to be quenched earlier, redder, more spheroidal, shaped by interactions and the steadily rising background density that strips their gas. Galaxies in thin filaments or at filament void boundaries keep forming stars longer spun up by cold flows and minor mergers. The web sets the initial conditions for galaxy ecology. When I walk a filament inward in my mind, I pass through the so-called splashback region of the cluster, a kind of caustic boundary where the orbits of recently accreted galaxies turn round for the first time. Inside of that, the cluster's atmosphere, the intracluster medium, becomes dominant. Outside, the filaments still own the geometry. The measured 3D path of a specific filament gives me a ruler to place these transitions with less guesswork. It lets me ask where star formation shuts down most abruptly, where ram pressure first bites, where infalling groups get tidally stirred, and whether those transition radii differ from lane to lane. I also want to push on how we actually turn two-dimensional lensing information into a three-dimensional story without fooling ourselves. In the simplest language, the field of tiny shape stretches is converted into a map of how much mass per patch of sky via an inversion. There's a standard recipe that relates the observed shear pattern to the convergence, which is the projected mass contrast. That recipe assumes the shear is small and that I know the geometry well enough to compute the leverage each background galaxy provides. Geometry in practice means redshift. Photometric redshifts distances estimated from colours are fast and plentiful but noisy. Spectroscopic redshifts distances from measured spectral lines are sharp but costly. In a result like this one, the spine of the filament is traced with spectroscopy, so I can be confident about what lies along a single, sinuous path in depth. For the background shape catalogue, I can rely more on photometry because I do not need individual perfection, I need the ensemble to be behind the lens. That mixture-secure depth for the structure I claim to be a filament plus broad statistics for the shape field is the balance that upgrades a hint into a reconstruction. I run through the systematics because they are the skeleton of trust. The instrument's point spread function can align galaxy images in a preferred direction. I model it with stars and subtract its signature. The detector can shear shapes subtly depending on where a galaxy falls on the chip. I calibrate that by injecting fake galaxies of known shapes into the data and measuring how the pipeline recovers them, then correcting the bias. Intrinsic alignments galaxies born a little lined up by the same tidal field I want to measure can masquerade as lensing. I dilute that by selecting sources far enough behind the lens and by comparing the signal when I rotate galaxies by 90 degrees, a null test that should erase gravitational shear, but not all systematics. Mass along the line of sight unrelated to the filament adds noise. I control that statistically and by using the 3D spine to define a mask that follows the structure rather than a rectangular box that would include more interlopers. I hear myself think, define the spine, because that's the conceptual heartpick, the coordinate system that the universe itself is using. The 3D extension also lets me talk about time, which is sneaky in cosmology, because every map is a light cone map. When I say the filament is 60 million light years long, I am mixing two ideas: its physical length in space at the epoch I'm observing, and the look-back time gradient along my line of sight. Light from the far end set out a bit earlier than light from the near end. Over tens of millions of years, that doesn't transform the structure, but over billions it would. So when we push these reconstructions to earlier cosmic times with deeper sources behind younger filaments, we will in effect be leafing through a flipbook of assembly. Early filaments were thinner and less braided. Later ones are thicker and richer in substructure. A survey that stacks many such 3D lanes by redshift will let me measure how the web itself fattens with age and how the infall rates onto clusters change as dark energy's push competes with gravity's pull. I don't want to lose the dark matter thread because mapping a specific filament in 3D is also a test of the cold and collisionless assumption that underpins the beautiful agreement between simulations and large-scale statistics. If dark matter is truly cold, meaning its particles move slowly compared to the speed of light and had very small thermal velocities in the early universe, then structure forms from the bottom up, small halos first, then larger ones by merging filaments, crisp nodes dense. If the dark matter had a bit of warmth, higher initial speeds, then small-scale power would be erased and filaments would be smoother and broader. If dark matter scatters off itself, significantly momentum exchange in dense regions would round off sharp features and produce cores with lower central densities. A single filament does not rule these alternatives in or out, but the combination of its thickness, its density profile, and the rate at which galaxies stream along it helps prune the family tree. I note to myself, prune the tree, because that is the tone I like, not declare victory, but cut away what doesn't fit. There's also a quiet triumph in how multiple, completely different messengers agree when we probe the same bridge. Pressure signals, measured via the subtle scattering of background microwave light by hot electrons, can pick up the gas threading, some intercluster filament. Stacked X-ray observations can glimpse the warm edge of that gas where it is densest. Dispersion measures from fast radio bursts count the total number of free electrons along a sight line, and when you have enough of them with secure distances, can map where the missing ordinary matter hides between galaxies. These are not the same thing as lensing. They are sensitive to different ingredients. When a lane lights up in lensing, as mass shows a whisper of pressure in microwave maps and sits under a thicket of enhanced radio burst, dispersions the triangulation becomes persuasive. Each method has its own gremlins. Together they cancel one another's blind spots. I also want to translate a couple of the mathematical phrases I use into handholds. When I talk about the growth factor, what I really mean is a curve over time that tells you how quickly a typical lump grows compared to the expansion of the universe. Early on, when matter dominates, growth is brisk because gravity has the stage mostly to itself. Later, as dark energy takes over and accelerates, the expansion growth slows on the largest scales because space itself is placing galaxies on a conveyor belt that is speeding up. You can feel that in the web. Voids expand, filaments lengthen, nodes still accrete along their nearest lanes, but the overall pace eases. The measured infall vectors in a mapped filament are a local snapshot of that global story. If I gathered many such snapshots at many distances, I could stitch together a movie of the universe's changing metabolism. I should linger on the choice of cluster, because that is a piece of observational wisdom. Not all clusters are equally good targets. A violently merging node with subclusters colliding can produce strong lensing features and complicated shear fields that make model building harder but also richer. A more relaxed cluster gives a cleaner lensing laboratory, but may have weaker, less active filaments. Picking a known growing cluster that sits at a crossroads is a strategic move. Go where the traffic is. Then aim the sharpest eye we have, measure carefully, and follow up with spectroscopy until the ribbon stands up in depth. It sounds straightforward. It takes years of patience and the choreography of multiple observatories. Let me talk about velocity fields in plainer terms, because peculiar velocity is jargon that hides something intuitive. Imagine painting the Hubble expansion on a black canvas. Every galaxy is carried away from every other in a smooth proportional way, with more distant ones receding faster. Now on top of that, add little arrows that show how galaxies move relative to this pure expansion because of local gravity. Those arrows point toward mass concentrations and along filaments. They are the peculiar velocities. Spectra give me those arrows' components along my line of sight by measuring tiny shifts in absorption or emission lines. When I chart many of those arrows for galaxies that lie in the same thin lane in depth, a melody appears. The arrows line up and tilt toward the cluster. It's a remarkably human moment. In a very technical analysis, suddenly the flow looks obvious. I return to the 60 million light years because I know big numbers can numb rather than illuminate. If I could slice that ribbon into kilometre-thick pancakes and weigh each one, I would be doing the exact same physics lensing does at a cosmic scale, mass per unit area, summed along the line of sight. The difference is that lensing does it with photons and geometry instead of with scales and hands. When I say the filament spans 60 million light years, I also silently say that our instrument's resolution, both in angle on the sky and in redshift, has crossed the threshold where that span is not a blur. We can trace curvature, not just detect presence. We can ask whether the lane kinks near infalling groups, whether it splits into strands like a braided river before it joins the node, whether it thickens as it approaches, as simulations often show. Those are not baroque questions. They are ways of matching reality to the physics encoded in the invisible particles we're trying to understand. There is an educational thread in all of this that I keep at the front of my mind because it anchors wonder to method. We do not see dark matter. We see the way it bends light. We do not see gas along most of the lane. We see how it pressurizes the cosmic microwave background or absorbs radio pulses. We do not ride with galaxies as they fall. We see the echo of their motion in tiny spectral shifts. Every piece is indirect. The strength comes from coherence. When three independent hard-won inferences point to the same ridge in the same place, with the same orientation, and with the same sense of flow, I allow myself to say simply that we have mapped a bridge, not guessed mapped. And then I can ask second-order questions, the kind that move a field. What is the scatter in filament densities around clusters of a given mass? Do thicker filaments feed earlier quenching? Does filament curvature correlate with recent mergers? Do the satellite galaxies that ride different lanes into the same node differ in metallicity and angular momentum? If the answer to even a few is yes, the web is not just architecture, it is biography. I also like to put our own neighbourhood in gentle focus, without overreaching. The local group sits on a minor strand, part of a basin that drains toward larger attractors. We live far from a behemoth, like the cluster I've been picturing, and that has shaped our history. Gentler tides, fewer cluster-scale shocks, a longer runway for star formation. We do not need a 60 million light-year bridge to explain the Milky Way's life, but knowing those bridges exist where the traffic is heavy lets me see our quieter suburb in context. And context for me is what transforms curiosity into comprehension. Before I close, I return to the craft, because the craft is the soul of this. The team that turned a scatter of faint galaxy shapes into a mass ridge, then into a 3D lane with motion, did it by layering checks on check. Rotate the galaxy shapes and the lensing signal should vanish. Split the data by color, by magnitude, by position on the detector, and the mass map should persist. Shift the source redshift cuts modestly, and the lane should not jump. Change the smoothing scale in the inversion, and the ridge should narrow or broaden as expected without wandering off. Compare to independent reconstructions with different shear estimators, and the spine should coincide. It is not flashy to say this out loud, it is necessary. I whisper to myself, necessary craft, because it keeps me honest. when I am tempted to let the beauty of the web do too much of the persuasive work. So, where does that leave me with a picture that is finally more than pretty? With a bridge of darkness 60 million light years long, whose arc I can trace in position and in depth, whose density I can estimate, whose traffic I can see flowing toward a growing city of galaxies, with a method that converts the tiniest stretches of distant galaxies into a census of gravity, with a research program that can scale from one virtuoso case to 1,000 ordinary ones as new telescopes open their eyes wider and deeper, with a universe that is not just a collection of isolated islands, but a continent with rivers and roads, and with the tools to survey those roads, not in poetry or simulation alone, but in measurement. And with a quiet recurring line in my head, still assembling, because the map is not only a map of what is there, it is a map of how it is becoming. I want to peel back one more layer and talk about why a map like this changes the questions I ask when I look at any galaxy, even one as ordinary as a little spiral far from a cluster. In the past, I might have described a galaxy's history by pointing to internal processes, gas accretion, star formation, feedback from supernovae and black holes, and then folded in local interactions like minor mergers. That picture is still right, but it is incomplete without the lane it rode in on. A galaxy is not born in isolation, it is delivered. When I hold the image of a 60 million light-year bridge in my mind, I start to think in terms of supply chain. Where did the cold gas that fed this galaxy's first starburst originate along the filament? How many times was it shock heated by group-scale halos as it drifted inward? Did the galaxy inherit its angular momentum primarily from the tidal torques exerted by the web's geometry aligning its spin with the filament's axis? As many simulations predict, I tell myself delivered and aligned, because it shifts my instinct from thinking of galaxies as self-made to seeing them as shaped by their roots. Spin is particularly fun to trace because it feels like a delicate fossil of early conditions. The idea is plain in words. If a forming galaxy sits in a tidal field produced by the surrounding mass distribution, those tides can twist the infalling matter and set a preferred rotation axis. Thin filaments produce a different twist than thick ones, and the handshake between the halo and the surrounding web can even flip with mass small halos, tend to spin along the filament, more massive ones perpendicular. When I have a measured 3D filament, I can test that directly by measuring spin proxies, like the orientation of stellar disks or the kinematic axis of gas relative to the lane. If the alignment signal depends on position along the filament or on proximity to the cluster's splashback boundary, then I know the web is not just scaffolding, it's a torque ring. I keep circling back to the warm, hot intergalactic medium because it hides a long-standing accounting problem in cosmology. We know from early universe measurements how much ordinary matter baryons should exist. When we inventory the obvious pieces, stars, cold gas in galaxies, hot gas in clusters, we come up short by a substantial fraction at low redshift. The missing baryons are expected to live in the filaments, shock heated to a few 100,000 to a few million degrees at densities too low to shine brightly. A 3D filament map gives me a template to stack X-ray data and to filter microwave background maps for the faint thermal imprint from hot electrons lifting the signal over the noise. It also gives me something to cross-correlate with fast radio burst dispersion measures. If sightlines that pierce the mapped bridge show systematically higher dispersions, then we are finally closing the baryon budget in a way that points to specific structures rather than to an undifferentiated IGM. Close the budget, I whisper, because it's one of those unglamorous essential tasks that turn a qualitative story into a quantitative science. There is a subtlety I want to own about the conversion from lensing signal to physical density that sometimes gets lost in the romance of the images. Lensing gives me a projected quantity. To lift it into 3 dimensions, I lean on the redshift distribution of both sources and structures and on an assumed geometry for the filament's cross-section. If I assume too rigid a shape, say a perfect cylinder, when the reality is slightly flattened or braided, I can bias the inferred central density or thickness. The defense is to treat the shape flexibly, to marginalize over a family of plausible profiles, and to check that the derived parameters are stable when I vary the smoothing scale of the inversion. This is not rhetorical caution. It is what keeps the result from over-promising. It's also where ancillary data save me. Spectroscopic redshifts don't just provide depth, they reveal substructure, like small groups riding along the lane that a purely smooth model would miss. When the 3D galaxy distribution shows a kink or a fork and the lensing ridge echoes it, I know my model's freedom is well spent. I want to talk about curvature because the reported filament doesn't run like a taut string. It bends toward us and then dives into the back of the cluster. Curvature tells a story about the larger gravitational landscape. Filaments curve when nearby mass concentrations tug on them, or when the underlying initial conditions seeded a twist on that scale. If I can measure curvature precisely and compare it with the distribution of neighbouring mass other clusters, big groups, thick sheets, I can test whether the web's geometry locally reflects the supercluster skeleton we model on large scales. In other words, does the measured bend line up with a known attractor beyond the cluster, or does it signal a nearby underdensity allowing the lane to drift? These are not idle geometrical fancies. They are sanity checks on how gravity knits structures across tens to hundreds of millions of light years. One of the pleasures of working with a defined 3D bridge is being able to carve the data cube along coordinates that mean something physically. Instead of slicing by right ascension and declination alone, I can define a curvilinear coordinate S along the filament spine and two orthogonal coordinates R1 and R2 across it. Then I can bin galaxy properties, star formation rates, metallicities, morphologies by S and by distance from the spine. If star formation shuts down sharply at a fixed R as I approach the cluster along S that hints at ram pressure thresholds. If metallicity shows a gradient along S that resets at the positions of infalling groups, that reveals pre-processing galaxies being transformed in group environments before they reach the cluster, I've always wanted to do that analysis with a clean lane. Now I can. Let me speak to the human side for a beat, because the road from idea to map is paved with small choices and hard-won techniques that rarely make headlines, but always decide outcomes. Choosing shape measurement algorithms that trade bias for variance appropriately. Building simulations with fake galaxies that mimic the real population sizes, surface brightnesses, and ellipticity distributions, so calibration applies. Designing spectroscopic masks that prioritize galaxies likely to trace the spine without starving the sample of diversity. Negotiating for telescope time across hemispheres and season, writing code that tracks uncertainties honestly through every transformation. I repeat to myself, track uncertainties, because the temptation to polish a result into certainty is everywhere, and resisting it is the culture I want to defend. There is also the question that lands in every public talk, what if dark matter doesn't exist? And what we're seeing is a modification of gravity. It's not a silly question. It's an invitation to check that the scaffolding story depends on a consistent gravity theory and not on an ad hoc fix for rotation curves alone. Lensing helps here because it tests gravity in the regime where it should reduce to general relativity on large scale. Many modified gravity models can mimic galaxy rotation curves without particle dark matter, but struggle to reproduce the lensing strengths of clusters and filaments without reintroducing some unseen mass in another guise. A 3D filament with a measured density and a measured infall pattern is a demanding playground for such alternatives. I'm open to the exercise. I'm also guided by the weight of converging evidence that a dark component acts as real mass in the equations Einstein wrote down. I owe you a clean explanation of how critical surface density turns geometry into leverage, because it is the key that unlocks mass from shape. If I could write it without symbols, I'd say this: imagine a triangle in space made by you, the lens, and the background galaxy. If the background galaxy is only a little farther than the lens, the triangle is narrow and the lens has short leverage to bend light. If the background galaxy is far beyond the triangle is stretched and the lens has a long lever arm, the critical surface density is just a way of encoding that lever arm into a number. For a given lens distance, as I pick sources farther away, that critical number drops, and the same measured shape stretch implies less surface mass to do the job. Conversely, if my background sources are closer than I thought, I will overestimate mass. That is why getting the source redshift distribution right matters so much, and why space telescopes that see into the infrared where distant galaxies are brighter relative to the sky are game changers. They give me more and more distant candles to weigh with. I've spent a lot of words on mapping, but I don't want to miss the chance to ask how the web's highways might affect the growth of the supermassive black holes that anchor galaxy centers. Gas funneled along a filament will not land isotropically on a galaxy. It will tend to join along preferred directions, likely stirring bars and non-axis symmetric features that torque gas inward. If those flows are stronger near nodes, we might expect more frequent or more powerful active galactic nuclei in galaxies still on the roads, in not just inside the city gate. With a 3D lane, I can test whether AGN incidence or accretion rate indicators spike at characteristic distances from the cluster or align with the filament's midline. It's a tidy example of how a structure we infer through gravity can echo in the light of feeding black holes. I want to be explicit about what 60 million light years does not mean. It does not mean the filament ends there. It means that is what we can trace coherently with the current data before the signal degrades or the geometry becomes ambiguous. In many simulations, the main bridges feeding a massive cluster extend hundreds of millions of light years before they branch and fade into the web. As our shape catalogues deepen and our redshift samples grow, the map length will lengthen. The first 60 million is a beachhead, not a boundary. In the near term, I can see a practical path to turning this from a singular feat into a small catalogue. Pick a half dozen massive growing clusters with hints of feed lines in existing lensing maps. Target each with deep, stable imaging observations to refine the shear field and with multiplex spectroscopy to carve a spine. Use the same analysis framework to reconstruct lengths, thicknesses, densities and flows. Then and only then compare across the set. Do fatter filaments correlate with higher present-day cluster mass growth rates? Do clusters in denser supercluster environments show straighter or more braided lanes? Do lanes with more subgroups, small knots along the way, deliver satellites with different morphological mixes? Theories have answers, data will referee. When I let my mind drift all the way out to the next decade, I picture something both grand and ordinary, a layer on an astronomical sky viewer, where you can toggle cosmic roads on and off, watching measured filaments appear as translucent. Ribbons between named clusters, each annotated with length, median over density curvature, and a little glyph showing the average infall vector. That sounds like outreach fluff. In truth, it would be the front end of a research database. You could query for all bridges of a certain thickness at a certain redshift cross-match with X-ray and microwave maps to find those with detectable gas, and select fields for deeper JWST follow-up to look for the earliest galaxies riding those highways. You could ask the database for all galaxies within a fixed distance of a spine to stack their spectra and hunt for environmental fingerprints. The romance of the web marries the prosaic power of a well-structured table. Before I draw a line under this pass, I want to distill the science into a simple, defensible conclusion I can carry in my pocket. We have, for the first time in convincing detail, reconstructed a specific dark matter filament in 3 dimensions as it feeds a massive galaxy cluster. The reconstruction rests on weak gravitational lensing to map projected mass on spectroscopic redshifts to trace a coherent spine in depth, and on galaxy kinematics to show infall along the lane. The map structure is at least 60 million light years long, gently curved and denser than the cosmic mean, by the few to 10-fold contrast expected for filaments in cold dark matter cosmology. The pattern of flow supports the picture of clusters still assembling via anisotropic accretion along the web. Systematic uncertainties, instrumental shear, intrinsic alignments, line-of-sight projections have been modelled and checked with standard null tests and with cross-validation against independent data sets. Alternatives in which modified gravity alone produces the signal face the same lensing and dynamical constraints and would need to mimic a dark component that acts like real mass. Within those guardrails, the results stand. It turns an architectural metaphor into a measured bridge, and that for me is the quiet joy here. Not that the universe is larger than I thought it always is, but that it yields to methods that honour both imagination and restraint. We imagined a web because simple physics told us small ripples would grow into large patterns. We built instruments that could hear the faint chord of lensing in the noise of real data. We layered distance and motion until a ribbon stood up in depth. We checked our work, admitted our uncertainties, and still the bridge remained. I think still the bridge because it captures both the persistence of the structure and the persistence of the people who mapped it. And somewhere beyond our galaxy's suburbs, matter is still gliding along that dark road toward a crowded city of galaxies. And we, with the patience learned from gravity itself, are learning to chart the roads as they are travelled. I want to press deeper into how we translate a picture of scaffolding into a set of quantitative levers we can actually pull, because otherwise the web remains a gorgeous mural rather than a working instrument. The first lever is topology, and I don't mean that as a flourish. A map like this can be measured the way a geometer would measure terrain. I can count peaks, saddles and voids. I can compute how many independent filaments connect to a node and how their connectivity changes as I vary the mass threshold used to define the ridge. In plain speech, if I slowly lower the water level on a relief map of mass, first only the tallest mountain tops stick out, then ridges emerge, then those ridges merge into a network that eventually percolates across the map. The exact way connectivity turns on a curve that tells me when isolated peaks link into chains and when chains stitch into a continent depends on the initial conditions of the universe and on how matter has grown since. The moment I have a clean filament reconstruction in 3 dimensions, I can place it in that family of curves. If a real filament appears thicker or connects earlier than simulations with a given kind of dark matter, predict that is not a shrug, that is a constraint. I carry next the lever of the tidal tensor in my head, even when I don't say the phrase out loud. Translate it like this: at any point in space, the gravitational field doesn't just pull, it stretches and squeezes differently along different directions. 3 principal axes describe that stretching and their relative strengths define whether I sit in a knot, a filament, a sheet, or a void. When I have a 3-dimensional lane with known curvature and a cluster with known mass, I can estimate those axes along the spine and across it. Then I can ask whether galaxy spins, satellite orbits, and gas flows line up with the least compressed axis, as they often do in simulations. If they do, the lane is not only a road, but the imprint of how gravity has been sculpting trajectories for billions of years. If they don't, I must learn why. Perhaps feedback processes have scrambled spins in dense stretches. Perhaps the lane's history includes a recent kink that reset alignments. I promised math in words, so I'll do that again for the idea of bias, which is a harmless sounding term with teeth. Galaxies are not perfect tracers of mass. They prefer to form where the potential is deep and the gas is coolable, which means they cluster more strongly than the underlying dark matter by a factor we call the bias. When I compare a lensing map, which responds to all mass, to a galaxy map, which responds to luminous peaks, the ratio between their contrasts across the spine measures that bias as a function of environment. To explain it without algebra, imagine I walk from the edge of the filament toward its center, stepping across equal intervals of distance. If the galaxy counts rise by, say, 10 units for every step, but the lensing inferred mass rises by only 7 galaxies, are 3 units more enthusiastic than mass. They are biased high in that environment. With one filament, the lesson is local. With many, I can chart how bias changes from void to sheet to lane to node, which then feeds back into how we interpret every galaxy survey ever made. I also keep a quiet ledger in my head for neutrinos because their ghostly mass leaves fingerprints on structure. Neutrinos stream almost freely through the cosmos and suppress the growth of small-scale clustering. The result stated in words is that webs in a universe with heavier neutrinos are ever so slightly smoother at fine scales than webs in a universe with lighter ones. That effect is modest and messy in any single field, but a catalogue of filaments with measured thickness profiles and density contrasts at different epochs becomes a neutrino balance sheet. I won't pretend one bridge fixes the neutrino mass, but the existence of a measured bridge sets the stage for using dozens to nibble at that question from the side, complementing cosmic microwave background and large-scale power, spectrum constraints with geometry in the late-time universe. Because I've been talking so much about lensing, I owe the complementary story of simulations that let me interpret what lensing sees without smuggling in my own wishes. The modern way to do this is not to run one Joule-like simulation and declare victory, but to generate large suites of mock universes that sample our uncertainties in cosmological parameters, in dark matter microphysics, and in the messy physics of gas stars and black holes. Then I put an imaginary telescope above the mock universe, degrade its images. In the same way, mine are degraded measure shapes with the same code and the same biases, and reconstruct filaments with the same inversion. The point is simple: to treat the simulated sky with the same fallibility as the real one. When a particular combination of parameters in the mocks produces filaments with the same length, curvature, density profile, and inflow speeds as my map, I haven't proven truth. I've narrowed the space of the plausible. Narrowed the space, I say to myself, because that is what progress looks like when the subject is as large as everything. There's an art to deciding what the same means when comparing a single glorious case to an ensemble of synthetic universes. I prefer summary statistics that survive noise and idiosyncrasy. The median overdensity within a fixed physical radius of the spine as a function of arc length S is 1. The half-mass radius across the filament, the distance at which half the mass lies inside and half outside, is another. The curvature vector's magnitude along S, smoothed over several megaparsecs to kill numerical jitters, is a third. The fraction of the total inflow carried by identifiable subgroups riding the lane, rather than by solitary halos, is a fourth. None is dramatic on its own. Together they make a fingerprint, and fingerprints are hard to fake. This is also the natural point to talk about error budgets, not as a dreary appendix, but as a living document. The mass map has shape noise calibration uncertainty and redshift errors. The spectroscopic spine has incompleteness. Some galaxies are too faint to measure, and selection bias. Some types are easier to target. The velocity field has projection noise and redshift space distortions that can make infall look like fingers along the line of sight if I'm not careful. Rather than hide these, I fold them into a forward model that tries to answer in plain language a single question. If the real universe contained a filament with this true profile and this true velocity field, how often would my pipeline recover the features I claim? If the answer is often, confidence rises. If the answer is rarely, humility rises, and I pare the claim back until the answer is honest. Pare it back, I remind myself, because the prettiest plots are often the ones most in need of restraint. The next layer, I want to peel concerns voids, which might seem like the wrong direction to go when we've just celebrated a filament. But voids are the other side of the same coin. A cleanly mapped lane lets me define the walls between which a neighbouring void expands. In gravity's calculus, what flows in somewhere must thin out somewhere else. A 3D filament reconstruction brackets the initial conditions needed to drive a particular adjacent void's growth. If I can measure the galaxy population's youth in that bordering void, its star-forming fraction, its low metallicity tail, I can tie the health of the cosmic countryside directly to the size of the highway next door. It's an environmental study at the 100 million light-year scale, a sentence that still makes me blink. Because this is a story of maps, I want to talk about coordinates again, but in a way that touches human practice. When I re-express a field in the coordinates of its own structure, arc length along the spine radius across it, and azimuth around it, I am not showing off. I am removing distractions. In a rectangular grid, the filament's thickness and the gradient of density across it are smeared by curvature. In spine coordinates, a narrow lane looks narrow, a widening looks like a widening, and a kink looks like a kink rather than a diagonal smear. It's like uncoiling a river in a cartographic projection. Once you do it, environmental trends pop out that were invisible before, do it wrong, and you invent features that aren't there, do it right, and the data tell you the story they wanted to tell from the start. I can feel a question forming about time variability, and I want to answer it before it's asked. On human timescales, filaments are frozen. But on cosmological timescales, they evolve, and their evolution isn't monotonic. Flows surge when neighbouring nodes merge quiet, when the lane has been recently drained and fattened, when minor tributaries align. When I look across redshift nearer universes and more distant ones are younger, and stack many lanes into bins of cosmic time, I can measure the web's changing metabolism. The growth factor I mentioned earlier becomes a measured slope on a plot where the vertical axis is typical filament over density, and the horizontal axis is the scale factor of the universe. In words, how much denser than average are lanes at half the present scale compared to now? Does that ratio care about the dark energy model, and could deviations whisper about new physics? I will not oversell it, but the possibility that roads can become rulers, standardizable features that carry cosmological information, is not fantasy. It is the inevitable next experiment, once we can map lanes with routine fidelity. Let me turn my eye back to the instruments for a moment and explain why I keep talking about space-based imaging as though it were a character in the story. Ground-based facilities are breathtakingly powerful, yet the atmosphere smears shapes in a way that is not only larger than the cosmic shear we seek, but also variable in time and across the field. We can model that smearing with point spread function reconstructions that dance as the dome breathes, but every model carries residuals. Hubble's stability is why this first 3D reconstruction feels like a watershed. Roman's promise is to scale that stability across huge areas. Euclid's gift is to bring space stability to a wide-angle view. On the spectroscopy side, Keck and Subaru have been our workhorses, and the next generation of 30-meter class telescopes with massively multiplex spectrographs will change the game by placing precise redshifts on galaxies that are now only smudges. Precise redshifts matter because they convert a beautiful picture into a velocity field you can compare number for number with a simulation's predicted infall. You might expect me to leave black holes at the centre of galaxies as a separate topic, but I won't. The accretion histories of supermassive black holes are braided into the lanes. I hinted at torque-driven inflows along preferred directions. I want to add that AGN jets themselves can couple back to the filament gas. When an active nucleus launches a jet into a denser medium aligned with the filament, it inflates cavities, heats gas, and could in principle thicken the lane's X-ray signature locally. This is speculative in detail, but it is testable in the aggregate crossmatch a catalogue of map lanes with radio maps and ask whether AGN with jets aligned near the spine show different lobe morphologies than those misaligned? If yes, the filament is not only a road, but an acoustic chamber in which black holes sing differently. I don't want to skate past the pedagogical value either, because clear maps change how students think. Before you've seen a measured spine, cosmic web is a metaphor that leans on simulations. After you've seen one, the metaphor is anchored. I can ask a student to calculate in words and then in numbers how the critical surface density shifts when I move the background source from a redshift of 1 to a redshift of 2, and then ask them which sources in a JWST field become most valuable shear tracers. I can ask them to reason why the splashback radius of a cluster might look different along and across a filament because the orbits of galaxies feel different tidal fields. I can ask them to sketch why the Zeldovich approximation, the early time solution where matter collapses first into sheets, then filaments, then nodes, still casts a recognizable shadow in the late time map. When I look in spine, coordinates, the point is not to revere a single map, it is to use it as a Rosetta Stone. I hear in my own voice a recurring refrain, still assembling, and I mean it as more than poetry. The web is not a static scaffold on which finished galaxies are hung like ornaments. It is a living infrastructure through which mass momentum metals and magnetic fields flow. Yes, magnetic fields, we now have hints from polarized radio emission and Faraday rotation that the intergalactic medium carries ordered fields at the tens of nanogauss level along some lanes. If that picture holds broadly, then filaments are also magnetic highways that can steer cosmic rays and alter how gas cools. That is early days science. A 3D mass spine with known geometry is the coordinate grid on which such measurements can be stacked, binned and believed. As I near the end of this pass, I want to compress the lesson into a handful of sentences a tired mind can keep. We took light from thousands of distant galaxies, and by measuring their tiny coherent stretches reconstructed where mass must sit along a line of sight dominated by a growing cluster. We then used redshifts to lift that two-dimensional mass ridge into 3 dimensions, traced a 60 million light-year lane that curves toward us, and then dives into the cluster and measured how galaxies stream along it. We quantified the lane's density profile, its thickness and its curvature. We tested for systematics with rotation splits and injected fate. We compared the fingerprint to simulations and found agreement with a cold, nearly collisionless dark matter skeleton. We turned a metaphor into a measured bridge. And I think that is the real gift to carry forward. Not that darkness has been forced to glow, it hasn't, but that geometry and patience have made it legible. I can now look at a quiet spiral and ask about the road it took. I can look at a blasting quasar and ask whether the lane is feeding it asymmetrically. I can look at a yawning void and ask how wide its bordering highways are. I can look at a merging cluster and ask whether the traffic surged last epoch because the lanes were kinked by a neighbouring attractor. Each of those questions is both imaginative and testable. That pairing, imaginative and testable, is the mark that a field has matured. So yes, still assembling in the sky as mass slides down dark roads into brighter cities, still assembling on our desks as we turn smears into maps and maps into catalogues, still assembling in our heads as metaphors become instruments. And somewhere out there, beyond the softness of our Milky Way's dust, a ribbon tens of millions of light years long keeps tugging, keeps feeding, keeps writing the slow script of structure while we patient and precise learn to read it. I want to push into the granular, almost tactile side of a dark bridge, because the more I picture it as an object with width, curvature, shear and flow, the more engineering instincts kick in. If I stand imaginatively at some point along the spine and look outward, the first thing I want to know is the radial force balance for a typical parcel of gas. Gravity pulls inward toward the spine, pressure gradients push outward, magnetic tension and turbulence add their quiet hands on the rope. In words, equilibrium at a given radius means the inward gravitational tug is matched by outward support. If the gas is very hot and diffuse pressure can shoulder much of the job. If magnetic fields thread the lane, the field lines curve around the spine and resist compression like elastic bands. Turbulence eddies fed by infalling subhalos and shocks adds an effective pressure that depends on the squared velocity of random motions. None of this is exotic. It is the same accounting a stellar astrophysicist does for a star's interior Only here, the scales are measured in millions of light years and the timescales in billions of years. The point of the accounting is to connect observables. If the X-ray brightness profile is shallow, but the lensing density profile is steep, non-thermal support must be doing real work. If the Sunyaev-Zeldovich pressure dips while lensing stays high, magnetic and turbulent cushions must be thickening the lane. I tell myself connect observables because that is how the invisible becomes interrogable. I also want to be clear about shocks because you cannot pour matter down a gravitational gradient without it slamming somewhere. Along a filament converging, flows at group scales produce quasi-cylindrical shocks that heat the warm-hot phase. In plain terms, gas streaming along the outskirts meets gas streaming from another tributary. Where they meet, the gas is compressed and heated. The shock speed is set by how fast the flows approach. The post-shock temperature scales with the square of that speed. If a flow comes in at 1,000 kilometers per second, the jump is enough to lift gas to tens of millions of degrees bright in X-rays near nodes. Farther out, where speeds are only a few hundred kilometers per second, the temperature rises to a few million degrees, too faint for most X-ray cameras, but perfect for leaving a pressure fingerprint on the microwave background. The beauty of a mapped spine is that I can place these shocks statistically at fixed fractions of the radial coordinate stack many fields and ask whether the shock radius shrinks as I move along S toward the node. If it does, the lane is not only a corridor, it is a series of standing waves, and I can measure their nodes. I keep a hand on the galaxy side because galaxies are the beads on the string that first persuaded us the string existed. There is a long-standing expectation from simulations that low-mass galaxies in the outer parts of filaments are more likely to be gas-rich and star-forming, while those nearer the node are more processed gas, strip stars, older morphologies, rounder. The real test with a 3D spine is whether those gradients survive when I measure distance, not as the crow flies on the sky, but as the fish swims along the current. If quenching correlates with arc length to the node and with perpendicular distance to the spine more strongly than with simple cluster-centric radius, then filaments truly set the ecological zone. I can test for pre-processing by looking for breaks in these gradients at the positions of infalling groups identified spectroscopically along S. If a group arrives, I should see a local uptick in quenched fractions and a twist in stellar kinematics as tidal stirring warms disk. If instead the gradients flow smoothly with no kink solo infall rules that lane, I don't want to neglect angular momentum bookkeeping because spin is as revealing as mass when it comes to origin stories. Picture a galaxy disk embedded in a halo sliding along the spine. Torques from the large-scale tidal field and from asymmetries in gas inflow tilt and twist the disk. In many simulations, small halos align their spins with the filament, while large halos flip to spins perpendicular to it, a transition that reflects how accretion geometry changes with mass. With a measured lane in 3D, I can rotate each galaxy into a frame where the z-axis points along the spine and ask a simple visual question. Do disks prefer to lay like coins stacked on the road or like wheels rolling along it? If the answer changes, with stellar mass or with local overdensity within the filament, I have caught the torque wrench in action. That is not romance. That is a direct test of a decades-old prediction turned into a yes-no plot by the availability of a physically meaningful coordinate frame. Let me put numbers into words for a moment because otherwise these pictures float. When I say the lane's central overdensity is a few to 10 times the cosmic mean, translate that as follows. Imagine a cube of space 1,000,000 light years on a side large enough to hold a small group of galaxies. If it is in a dense place, almost empty. If it is in a void, fill that cube with the average matter of the universe and you get 1 unit. Move the cube to the center of a filament and measure again. You might find 3 to 10 units in the same volume. That extra mass is mostly dark matter by the universal 5-to-1 rule between dark and baryonic matter, with a frosting of gas and galaxies. The gradient from the center of the spine to its edge is not sharp like a wall. It falls smoothly, often roughly as a power law softened by a core. If I have enough signal, I can fit that slope in real data and compare it with the family of slopes that different dark matter microphysics produce. Warmer dark matter with higher early velocities tends to flatten the inner slope. Self-interacting dark matter can round it further. Cold collisionless dark matter tends to give steeper, crisper profiles. One lane honestly measured is a partial vote. Many lanes fairly sampled across environments and times are a tally. I also want to ask the practical question, how do we scale this beyond the 1 or 2 fields that we can lavish with Hubble time and deep spectroscopy? The answer is a layered strategy. Use wide-stable space-based weak lensing surveys to flag cluster fields with significant elongated mass ridges. That gives candidates. Use ground-based multiplex spectroscopy to stitch a sparse but reliable 3D spine through the candidate's anchoring depth. Then target a subset with deeper imaging and denser redshift sampling to calibrate the relation between quick-look lensing strength, galaxy density, and true mass profile. Once calibrated, the quick-look metrics become predictors, letting me infer basic lane properties for hundreds of fields where I cannot afford intensive follow-up. It is the same logic as using type Ia supernovae. Calibrate a few perfectly, then use many approximately and propagate uncertainties honestly. Calibrate a few, use many, I repeat, because that is how an art becomes a survey. There is a compelling role here for fast radio bursts, and I want to explain it cleanly because it sounds like a magic trick when it's just clever statistics. Each burst is a millisecond-long flash of radio waves from a distant source whose signal arrives smeared high-frequency waves come slightly earlier than low-frequency waves. The amount of smear is the dispersion measure, and it counts in plain language the total number of free electrons along the path. If I collect many bursts with good positions and known host redshifts and cross-correlate their dispersion measures with the locations of mapped filaments, I can ask whether sightlines that pierce lanes are on average more smeared than those that don't. If yes, and if the excess scales with distance from the spine, the way a cylinder of ionized gas would I have weighed the elusive warm-hot baryons in a way complementary to X-ray and microwave probes. It is not necessary to resolve a filament in an individual burst. Stacking many sightlines against a 3D road atlas is enough to expose the excess. Stack many sightlines, stack many lanes, that phrases the bridge between ideas and an executable plan. I should also talk about curvature again, because the measured bend of the lane contains memory of its neighbourhood. Imagine drawing the large-scale gravitational potential as hills and valleys in a landscape. Filaments trace the valleys between hills. If another hill, a neighbouring cluster or supercluster wall sits nearby, it will tilt the valley and curve the river. With a 3D map, I can compute the curvature vector along the spine and ask whether its direction points toward known mass concentrations. If it does, good. If it does not, perhaps we are missing a wall of mass in our luminous catalogue, or perhaps line of sight projection is sneakier than we thought. This is the part where consistency checks feel like detective work. Lensing says the road bends northeast, galaxy density maps say nothing's there, microwave maps hint at a pressure ridge. Together they whisper that a dim wall rich in dark matter poor in starlight lies just out of obvious sight. That is how cross-discipline astronomy works. When it works best, each method nudges the others toward a fuller truth. Because I've been careful with systematics, I owe one more plain-spoken note on them: intrinsic alignments. I said earlier that galaxies can be born a little lined up by the same tidal field we want to measure. In a filament, this is not a nuisance, it is also a signal. The trick is to separate the part of the alignment that informs us about the tidal skeleton from the part that masquerades as lensing. The standard way is to use redshift slicing. The alignments matter most for galaxies physically near the filament in depth. Lensing affects galaxies behind it. If I split sources into near and far using photometric redshifts and find shape correlations in the near sample, those are intrinsic. If I find them in the far sample and not in the near, that's lensing. Doing both, I can both subtract the contaminant and learn something about how the lane's tidal field has imprinted galaxy shapes. Subtract and learn, two verbs for the same dataset. I want to swing back to cosmology broad brush for a minute, because roads can in principle become rulers. The abundance and thickness of filaments as a function of redshift respond to the overall growth rate of structure, which is a lever on dark energy. In words, in a universe where gravity wins, earlier lanes thicken and nodes grow faster. In a universe where accelerated expansion pushes earlier lanes fatten more slowly. This is a gentle effect. It will not rival the raw power of baryon acoustic oscillation distances or supernova Hubble diagrams soon. But it is independent and geometrically flavoured, and independence is gold when you are testing a pervasive phenomenon like cosmic acceleration. If we can standardise some filament observable a median over density at a fixed percentile of the mass profile, say, and show it correlates tightly with cluster mass and cosmic time, then we have a supplementary probe. Supplementary, not solitary. I will not oversell it. But nature rarely gives us just one ruler. The wise strategy is to carry a kit. Let me be explicit about Milky Way context without overreaching. We are in a quiet neighbourhood on a minor lane, falling toward a local basin, sometimes called the Laniakea supercluster region. with gravity tugging gently toward the Great Attractor Complex and beyond. Our road is a footpath compared to the highway feeding a behemoth cluster like the one we mapped, and that difference has written itself into our history. The Milky Way retained gas longer, built a steady disk, and avoided the harrowing tides of a rich cluster core. When I look up at the tranquil plain of our galaxy, I can see now not only a product of internal processes, but a beneficiary of modest infrastructure. That is, context without hubris. The road you take matters, but it does not dictate every step, because this has all been quite grand. I want to end this round with something beautifully mundane, a worked example in words. Suppose I pick a point 50 million light years from the cluster along the spine, with a measured surface mass density from lensing that corresponds to 5 times the cosmic mean within a central cylinder a million light years in radius. I observe stacked across many similar points a mild excess in fast radio burst dispersion measures of say 30 units above lines of sight that miss the lane. 30 units means 30 extra electrons per cubic centimetre integrated over a megaparsecant scale path, which in turn says there is a column of baryons roughly consistent with the fraction expected to hide in the warm-hot phase. I also see in microwave maps a small but coherent thermal Sunyaev-Zeldovich decrement aligned with the spine, and in deep radio polarimetry a hint of enhanced Faraday rotation evidence for microgauss level magnetic fields spread over hundreds of kiloparsecs. Put those together and I can write a sentence with numbers behind every noun. The lane carries a warm hot plasma at a few million degrees, threaded by ordered magnetic fields, with a baryon column sufficient to close a portion of the local budget, all wrapped around a dark matter core that defines the potential. That single sentence is the prize. It is not poetry, it is a ledger. So where am I? As I step back from the table, with a bridge I can now treat as an object, not just a motif, with coordinates that respect the object's own geometry so that trends sharpen, with cross-checks that turn systematics from threats into sources of extra information, with a growth of structure intuition that says roads can carefully act as secondary rulers, with a plan to scale from the painstakingly mapped few to the approximately mapped many, and with a sense that the warm, hot medium's hiding places are finally being cornered, and above all with that refrain still in my ears, still assembling because the web is not wallpaper. It is a living network of roads that carry mass momentum, heat metals, magnetic fields, and history. We have learned to listen to those roads by reading the tiny stretches of distant galaxies, by counting electrons in brief radio whispers, by weighing pressure imprinted on ancient microwave light. Listen and read, listen and read. And somewhere along a dark curve, tens of millions of light years long, matter keeps whispering its way inward, writing a story we can now follow in 3 dimensions with numbers with care. I want to take one more step from map to mechanism, because once a structure stops being an outline on a slide and becomes an object with measurable properties, you can start asking causal questions in the same tone you'd use for a wind, tunnel, or a watershed. The first causal thread I pull is the mass sheet degeneracy, which sounds like jargon but is simply a reminder that lensing by itself cannot tell whether I've added a uniform blanket of mass everywhere on top of the true distribution. In words, if you drape a perfectly even sheet over a landscape, the relative hills and valleys look almost the same to lensing. Shapes care about gradients more than absolute levels. Breaking that degeneracy is part art, part data. Magnification is the art. A heavier sheet makes background galaxies not only sheared but also slightly larger and brighter, on average changing their apparent number count. Kinematics is the data measured. Infall speeds along the lane demand a certain depth to the gravitational valley, and a uniform blanket cannot provide directional flow. Put the two together, shape and size, shear and magnification, flow and curvature, and the filament's absolute mass scale tighten. I repeat to myself, tighten the scale, because it's the moment a pretty ridge becomes a waggable bridge. I keep turning the filament in my hands, figuratively, and I want to talk about the E and B in the room. When many tiny stretches of background galaxies combine, they can be decomposed into 2 pattern families. One is curl-free, the natural signature of gravity's tidal field. The other is divergence, free, a swirl pattern that pure lensing does not produce at leading order. In words, gravity makes E modes, but not B modes. Any significant B mode power in my reconstruction is a red flag pointing to systematics, imperfect, point spread modeling detector, quirks, misestimated redshift. A clean filament map that shows E without B at the expected ratio is a sanity test passed. It's not philosophy, it's a quality gate that lets me sleep at night. Because I refuse to leave the math as a talisman, I'll translate one more step about how flows become numbers. The infall pattern along the lane can be summarised by a simple human picture. Take the average redshift of galaxies at a fixed distance along the spine, subtract the Hubble expansion you expect for that distance, and what remains is coherent in or out motion. The profile of that residual along the lane, small in the outskirts, peaking where the cluster's pull is strongest, becomes a direct measure of how much mass sits downstream. If the peak is too modest for the lensing mass I've inferred, then perhaps anisotropic orbits or projection effects are blurring the signal. If the peak is too strong, my mass map may be underestimating density because of a conservative shape calibration. Flow and mass must sing the same melody, or someone is off key. Make them sing, I tell myself, because cross-checks are the metronome of honest inference. What surprises me most once I let the measurements breathe is how quickly this becomes a story of thermodynamics and chemistry as much as mechanics. The warm, hot, intergalactic medium along a lane is not a sterile bath. It's enriched by metals blown out of galaxies, seeded with dust grains fragile enough to be destroyed by sputtering, but hardy enough to ride for a while, threaded by magnetic fields stretched and folded by shear. When I take a measured spine and co-add thousands of galaxy spectra at fixed distances from it, I can watch subtle absorption features, oxygen at specific ionization, states neon, even nitrogen growing or fading. Those are chemical fingerprints of where and how gas has been pre-processed before it reaches the cluster. If metals spike at the positions of infalling groups, then galactic winds have been recycling into the lane. If instead metal lines rise smoothly toward the node, the enrichment is a long, steady drizzle. Drizzle or spikes, I whisper, because either way, the lane is not simply a conveyor belt, it's a mixer. I keep a separate page in my notebook for angular momentum, because we've learned the hard way that spin transports history. The alignment of disk axes with the filament's direction is not just an aesthetic curiosity, it is a fossil of how torques accumulated over cosmic time. In plain language, if small galaxies tend to spin along the lane and large ones flip their spin to be perpendicular, that crossing mass tells me when the geometry of accretion changed. A clean 3D spine lets me measure that crossing mass in the real sky, not just in simulations. If the crossing mass near a rich node is lower than in the quiet countryside, environment is accelerating the flip. If the crossing mass drifts with redshift, the balance between smooth inflow and clumpy group infall is evolving. Spins are compasses, compasses mark routes. I also want to bring in the quiet partner that always shares the stage with mass time. A map at one epoch freezes a process that is ongoing. The obvious route to thaw it is redshift tomography, repeat the same measurement at different look-back times, then line up the frames. But there's a human trick that helps before we can fill the whole timeline. Within a single well-mapped field, the lane's own curvature and the population gradients along it can act as pseudo-time markers. Infalling groups leave caustic features edges in phase space, whose positions, relative to the splashback radius, mark how many orbits have passed since their first plunge. Count those edges along the lane and you've timestamped segments of the road. Timestamp segments let you compare control for dynamical age, where quenching metallicity shifts and AGN triggering are strongest. It's forensic cosmology, and a third dimension is the difference between guesswork and a coroner's report. Because the web carries electricity in the form of conducting plasma, I can't quite resist the magnetism thread. Radio polarization maps, when stacked on measured spines, can reveal coherent Faraday rotation that flips sine across the lane field lines that wrap the filament. Will rotate the polarization one way on one side and the opposite way on the other. Even a hint of that pattern, when aligned with a 3D spine, turns a suggestion into a geometry. Magnetic fields matter because they bias how gas cools preferentially along the field and how cosmic rays stream. If the field is ordered, heat conduction changes from isotropic to channeled, and channeled conduction can erase temperature gradients the way a river erases a sandbar. Dark scaffolding, luminous chemistry, magnetic plumbing. I like how the picture broadens as the map sharpens. Let me go practical for a few paragraphs, because scaling from showcase to survey will not happen by wishing. We have to automate without losing rigor. That means shape measurements that carry self-calibration, where the pipeline injects fake galaxies with known ellipticities into real images in real time, learns its own biases, and corrects them contextually, rather than with a single global number. It means photometric redshifts that carry full probability distributions for each source, not just best guesses, so the lensing inversion can weight each galaxy by the right geometric lever arm. It means spectroscopic target selection that is adaptive. Start with a coarse spine compute, where the uncertainty in curvature or density is largest, and place the next masks there, the way a surveyor tightens a triangulation net by measuring the longest, least certain baselines first. It means Bayesian hierarchical models that allow each filament to have its personality while borrowing strength from the population to constrain shared parameters like the typical inner slope or the dispersion in thickness at fixed cluster. Mass, none of that is romantic. All of it is what turns a field from a one-off into a factory of insight. I also want to give due to topology as a discipline rather than a metaphor. Minkowski functionals, global descriptors of shape that count volume, surface area, curvature and connectivity, are not just for pretty contour plots. If I measure them on the lensing-derived mass field and compare to MOCs, I have a summary statistic indifferent to many nuisances that plague local measures. In words, how many separate ridges exist above a certain mass threshold? How quickly do they merge? As I lower the threshold, how many holes appear in the network as it percolates? A single filament is a local triumph. The way filaments connect and merge as you vary the waterline is a cosmological test. Lower the waterline, watch an island chain become a peninsula, then a continent. The exact water levels at which those transitions happen encode the initial randomness of the early universe and the amount of smoothing that neutrinos and dark energy imposed later. It's a different conversation than counting clusters, and I like different, because you might be hearing an echo of the Zeldovich approximation in the background collapse along one axis to make sheets along two, to make filaments along three, to make nodes. I'll say plainly that a 3D spine is the late time descendant of that early time math. If I unroll the lane into its own coordinates and measure the density and velocity gradients, I can fit them with simple, physically motivated forms that are direct continuations of the Zeldovich picture with non-linear corrections. The point of doing that is not to show off elegance, but to gain intuition. When the fitted strain along the spine is high and the transverse compression low, I expect spin alignments to be preserved. When the transverse compression ramps up, flips loom. If the fitted strain correlates with the local curvature sign, looks for me like the lane is beaded with groups and turns, and that's where shocks should be strongest. Those are testable predictions written in words on the back of a notebook page, grounded by a map. I will not skip the elephant in the room, alternatives to particle dark matter. Modified gravity theories often appeal because they explain some galaxy-scale phenomena with fewer unseen entities. But lanes tied down in lensing and kinematics are a stern test. You must reproduce a curl-free shear pattern with the right amplitude, a magnification signal that matches it, and a flow field whose accelerations equal the gradients of the same potential that lends the light. In words, the same gravity that bends photons must pull galaxies. That unity is hard to fake across scales, though not impossible in carefully tuned models. A 3D filament doesn't end the debate, but it raises the entry bar. Raise the bar, I tell myself not to be exclusionary, but to be faithful to the coherence data demand. I want to land this round with a human scale walkthrough because the numbers can recede into grandeur if I let them. Imagine you and I standing imaginatively halfway down the measured lane, 50 million light years from the cluster. The lensing map tells us we're inside an overdensity 5 times the cosmic mean within a cylinder a million light years across. Spectra of the galaxies around us show a gentle headwind. On average, they are sliding toward the cluster at a few hundred kilometers per second relative to the Hubble flow. Microwave maps whisper a small pressure dip aligned with our axis-hot electrons imprinting their signature on ancient light. A stack of fast radio burst sight lines that pass near our spot shows a modest excess of dispersion, the count of free electrons ticking higher by a few tens relative to sight lines that missed. In deep radio polarization, a faint pattern of Faraday rotation flips sign across the spine, hinting at wrapped magnetic field. In optical light, the disks of small galaxies tend to be oriented like coins laid along the road. Larger ones start to cant like wheels. Farther toward the cluster, quenched fractions rise. Behind us, the sky opens into a more forgiving countryside. None of these alone would convince me I stand on a bridge of darkness. Together they leave me with the comfort of converging truths. So where does that leave me beyond the pleasure of a map and the rigor of its checks, with a compact, defensible set of levers I can carry forward? Shear plus magnification to fix absolute mass, E without B to police systematic. Flow profiles to tune depth, chemical and pressure fingerprints to weigh the warm-hot phase, spin alignments to date torque histories, topology to compare network-level statistics against models, curvature vectors to tie local bends to the larger gravitational landscape, hierarchical modelling to scale from the joule to the catalogue, and a steady discipline of null tests, injected fakes and split samples so that beauty never outruns truth. I keep the refrain still assembling, not as a flourish but as a working description. The lane is still assembling as groups bead along it and plunge. The cluster is still assembling at the node. Our methods are still assembling as we fold more messengers into the same spine. Our catalogues are still assembling as wide surveys turn singular feats into routine products. Still assembling. And underneath that repetition is a simple confidence that a universe whose deepest scaffolding is dark can nevertheless be read by the light. It bends the flows, it guides the heat, it imprints and the spins, it twists. We have learned the alphabet, now we are writing sentences. And somewhere silently, a ribbon tens of millions of light years long continues to carry mass and memory inward while we with patient instruments and careful sums keep learning to read its slow script. I want to lean into the last quiet frontier that a map like this opens up, using a measured lane to stitch together stories across scales without breaking the thread of causality. I've kept saying bridge and road because those metaphors are true, but I also hold in my mind the image of a living river, fed by tributaries, braided by bars, guided by banks, and I ask hydrology-style questions in a cosmological key. Where are the eddies? Where are the confluences? Where do sediments, metals, dust, magnetic helicity get trapped? And where do they flush downstream? If I stand a respectful distance from the node and watch imaginatively over a few billion years, I'd expect to see groups arrive like log rafts peel apart under tides and seed the cluster outskirts with galaxies that remember in their stellar kinematics and chemical clocks the rhythms of their upstream life. Remember upstream. Remember upstream, I repeat it, because the reason to celebrate a 3D spine is not only that I can weigh it, but that I can track biographies along it. The biographies begin with gas, because gas writes the script that stars read. In a curving 60 million light-year lane, you can imagine cold streams threading a warmer sheath, a hierarchy of flows whose crosstalk sets the supply schedule for galaxy disk. If the cold component is clumpy bound up in small halos and filaments within filaments, then star formation in riders may be punctuated a sequence of bursts keyed to encounters. If the cold component is smoother, then the disks breathe steadily until the pressure of the cluster's atmosphere steals their wind. The way to discriminate is observationally prosaic and spiritually satisfying. Measure the scatter in star formation rates at fixed mass and fixed position in the spine coordinates. High scatter far from the node means clumpy supply. Low scatter means smooth. Stack spectra to catch weak emission lines that trace recent fueling. Add the kinematic signatures of bars and warps, which often betray recent gas inflow. All of it is small individually. All of it adds when the coordinate system respects the road. I want to talk openly about energy because nothing falls forever without transforming some of its gravitational energy into heat and radiation. The inflow along the lane is a power source, and I can budget it in words. Take a parcel of mass sliding toward the node. As it descends the gravitational well, it gains kinetic energy. When it shocks against counter streams, against a thicker atmosphere, that kinetic energy turns into thermal energy. Some leaks as X-ray photons if the gas is hot enough. Some goes into long wavelength pressure fingerprints on the microwave background. Some stirs turbulence that later decays into heat. Some may amplify magnetic fields by stretching and folding them. The total power available depends on the mass flux, how much matter per unit time crosses a ring around the spine, and on the depth of the potential. If my lensing plus kinematics yields a mass flux of a few hundred solar masses per year per megaparsec of lane, and the potential drop into the cluster corresponds very roughly to a few hundred kilometers per second of speed gain, then the power is the product of mass flow and the square of that speed. Translate that into plane units, and you're talking about luminosities rivaling small galaxies spread volumetrically along the road. We rarely frame it this way, but a filament is a power line. Because energy follows paths, I can't resist the question of how that power couples to the galaxy-scale engines that light up intermittently as active galactic nuclei. If the lane supplies gas preferentially along the midline, that geometry pushes bars to grow inside disks and bars torque gas inward. Inflow feeds black holes flare and jets carve cavities. The cavities push back heating and displacing gas, sometimes halting star formation. The causal loop sounds clean, but nature is rarely so obliging. That's why a 3D spine is precious. I can align many fields cut by arc length to the node and radius from the midline and measure the incidence of AGN, the power of radio jets, the ages of stellar populations, the entropy of intragroup gas. If those curves crest at characteristic distances, I have a lever. If they do not, the feedback loop is either more stochastic or more local than my lane scale intuition suggests. Either way, the measurement is finally posed in coordinates that match the physics. There is a subtle craft in how I keep human scale errors from masquerading as cosmic truths, and I want to show that craft rather than assume it. When we infer a velocity field along the spine, we subtract the Hubble expansion using a background cosmology. If I use the wrong cosmological parameters, say I assumed a lower matter density or a different dark energy behavior, I would imprint a false gradient along the lane. The cure is simple and robust. Treat the background cosmology not as a fixed input, but as a parameter with priors, and ask whether the same values that fit the lensing distances also bring the flow profile into tune. In words, the cosmology that builds the triangle of observer lens source in lensing must be the same cosmology that sets the Hubble slope I subtract from redshift. When one cosmology makes both maps sing together, confidence increases. Make them sing together, I keep that as a private refrain, because harmony between independent effects of the same parameters is where cosmology proves itself. I'm going to admit a fascination with something that sounds esoteric until you see it once: caustics in phase space around clusters, the sharp edges that appear when you plot galaxy velocity versus cluster-centric distance. Those edges mark the splashback radius, the place where recently accreted orbits turn around for the first time, and they shift when accretion rates change. What matters for the lane is that the splashback feature is anisotropic. It sits closer to the centre along the filament than perpendicular to it, because infall is more coherent along the road. The measured spine lets me tilt the data so that anisotropy becomes a clean measurable trend rather than a smear. When I see the edge move inward along S, I know the recent accretion has been vigorous on that side. When I see it move outward, the lane has quieted. It's a near real-time gauge of traffic in a universe where real-time is not hours. I don't want to skip the tiny passengers that ride the web dwarf galaxies and the faint streams of stars that peel off them. Dwarfs are vulnerable to tides and to the ram pressure of ambient gas. In a spine coordinate system, I can count how many dwarfs survive to a given distance from the node versus how many are shredded into streams. If the shred rate is higher along the midline, the lane is denser or more turbulent than the flanks. If the shred rate rises in step-like increments, I'm catching the fingerprints of group arrivals. Those streams then become dynamical tracers. Like tea leaves in a cup, their orbits trace the swirls. The notion of using them is simple streams align with the local gravitational potential's shape, so measuring their curvature and dispersion tells you about the gradient across the spine. It's soft data, but when your map already fixes the gross structure, soft data can sharpen edges. I want to face directly the alternative that dark matter is something stranger than cold and collisionless, but still particulate self-interactions that are rare, but not zero, for instance. A lane is an amplifier of such microphysics. In a self-interacting scenario, particles can exchange momentum when they meet, and in a sustained flow that can round off the core more than in a purely collisionless case. The clue would be a central density profile that refuses to steep into the cold standard even when systematics are under control, coupled with a thickness that is larger than expected at fixed mass flux. Because lanes stir for billions of years, even a modest cross-section per unit mass can accumulate noticeable effects. I cannot declare a detection with one bridge. I can design a test with 10 and a survey with 100. The discipline here is to pose the question in the language of profiles and flows, not in the poetry of "it looks softer," because softness must clear the bar of measurement. I also feel the tug to bring the story back home, not to shrink the universe, but to make the scale jump without losing rigor. The local group thread I sketched earlier becomes more than context when I ask whether our modest lane imprinted any alignment or quenching trends here. Satellite galaxies around the Milky Way and Andromeda do show anisotropies and planar alignments that have sparked debate. If our minor road delivered satellites along a preferred direction, some of that pattern could be fossil geometry. The test is not to retrofit every anomaly to a lane, but to ask whether the orientations of satellite planes and the directions of known streams align with the Bayesian scale flow measured by reconstructions of the local velocity field. If yes, the big and the small rhymed. If no, the small sang its own song. Rhymed or solo, the point is that I can now frame the question cleanly. Because I've kept the tone resolutely empirical, I'll allow myself one step back to first principles to show how close we are to a clean, almost pedagogical chain from early to late. The Zeldovich picture says, start with a nearly uniform density field peppered with small Gaussian ripples. Expand the universe, let gravity pull harder where it starts slightly denser. Collapse first along one axis to make sheets, then along a second to make filaments, then along a third to make nodes. Lanes and nodes remember the initial tidal field's principal axis. A measured spine lets me infer approximately those axes in a late-time, non-linear world by fitting the density and velocity gradients along and across the road. When the fit recovers in words strong compression across gentle stretching along, I hear the early mathematics echoing. It's not nostalgia, it is continuity. The initial conditions that the microwave background measured are not just ancient trivia. They are still writing in the script we are reading along this bridge. I'm going to be blunt about the sociology of this because science is human work and human choices shape what we learn. Maps like this arrive because teams decide to spend precious telescope time on hard, low glamour tasks, calibrating shapes, filling spectroscopic masks to completeness in ugly regions, checking null tests no one will applaud for, passing. They also arrive because we build shared tools rather than one-off pipelines so that the next group can iterate instead of reinvent. If we want an atlas of lanes rather than a scrapbook, we need the unglamorous agreements, common formats for shape catalogues with per-object redshift probability distributions, open mock skies that reflect the foibles of real data, cross-survey photometric calibrations that keep colour-based redshifts from drifting. I keep a private mantra, make boring things beautiful, because when we do the boring parts well, the beauty arrives faithfully. There is an almost meditative satisfaction in closing the loop with numbers you can say aloud. The filament is at least 60 million light years long, gently curved, with a central overdensity, a few to 10 times the cosmic mean, within a cylinder, about 1 million light years in radius. Galaxies within it stream toward the node at a few hundred kilometers per second relative to the Hubble flow, a pattern that peaks closer in where the cluster's well deepens. Warm hot gas along the lane leaves a small pressure imprint on the microwave background and likely contributes a modest excess to fast radio burst. Dispersion measures tens of units on average, which translated means a column of free electrons consistent with the census of missing baryons. Magnetic fields at microgauss to tens of nanogauss levels would be enough to leave detectable Faraday rotation signatures when stacked in the right coordinates. Disk galaxies show hints of spin alignment that flip with mass, a fossil of torque history that spine coordinates make testable. None of these numbers is heroic, all of them are earned. I do not think the ending should be a flourish, but a promise. The promise is that with Roman and Euclid mapping weak lensing across huge fractions of the sky with JWST and the next generation of ground-based giants, placing precise redshifts on faint riders with radio arrays, localizing fast radio, bursts by the thousands, and with the microwave telescopes sharpening their pressure maps, the solitary bridges we celebrate now will become a network we can query the network, how thick are lanes at redshift 1 compared to now, query the network, do clusters in busier supercluster neighborhoods have straighter roads, query the network, does the typical flip mass for spin alignment drift with cosmic time. Each query is a line of code backed by a decade of patient craft. So I stand mentally again on that dark ribbon, halfway to the city of galaxies. The sky is still and not still. Shapes of distant candles carry the weight of everything between us and them. Spectral lines hold small shifts that when stacked become winds. Ancient microwave light hums with a faint lane-shaped pressure song. Millisecond radio flashes count electrons with the implacability of accountants. Disks tilt like coins and wheels. Dwarfs shiver and sometimes dissolve into glittering threads. The numbers are small, the patience large, the reward proportionate. And over all of it, I let the same gentle refrain play, still assembling because the bridge is still feeding its city, the city is still swallowing its meals, our catalogues are still finding their legs, our methods are still learning their grammar. Still assembling. And in that steady chant there is nothing mystical, only the pleasure of comprehension earned. A universe whose deepest scaffolding is dark, made legible by the light. It bends the flows, it guides the heat, it imprints, and the spins it twists. Mapped now not as a metaphor but as a measured road we can follow with numbers, with care, with joy, I want to finish the arc by stepping straight into the lab notebook of the near future, because the power of a single measured lane only truly arrives when it becomes the seed crystal for a whole catalogue, a whole way of thinking. I open that notebook and the first page is a simple question written in big letters. What are the minimal measurements that turn a suspected ridge into a physically characterized bridge? Minimal matters because time on great telescopes is finite and the universe is lavish with possibilities. My answer, written after too many late nights, is a three-part recipe I can say aloud. First, a shear map that is clean enough to expose an elongated overdensity with a significance that survives all the null tests. Rotate galaxies by 90 degrees and the signal dies, split the sources by colour and the signal persists. Scramble the positions and the ridge vanishes. Second, a spectroscopic spine dozens to hundreds of precise redshifts along the crest to prove that the structure is truly one thing in depth and not a projection of many. Third, a flow trace, peculiar velocities that line up along the lane toward the node. Shear spine flow. Say them quickly and they sound like a mantra. Say them slowly and they sound like engineering requirements. I keep my eye on magnification because it is the sibling of shear we sometimes treat like a cousin. Lensing doesn't only stretch shapes, it also changes the apparent sizes and brightnesses of background galaxies. In words, a heavier lens makes distant galaxies look a tiny bit larger and a tiny bit brighter, so the number of galaxies you count above a fixed size or brightness threshold shifts. The trick is that astrophysical noise galaxy evolution clustering can mimic some of that shift, so you don't lean on magnification alone. But when magnification and shear are measured from the same images and both point to the same ridge with the correct ratio for the geometry, they act like a second independent lock on the same door. Locks matter because they keep you honest when a single method could be seduced by systematics. I remind myself 2 locks, 1 door whenever the map looks too tidy. There's a page in that notebook labelled priors in thick pencil, and I leave it there to warn myself against importing answers into questions. If I assume every filament is a perfect cylinder with a particular inner slope and outer taper, I will recover perfect cylinders with that slope and taper. The cure is to let data breathe. I allow the cross-section to be elliptical. I allow the centre to wander a little as subgroups bead the spine. I allow for a braided structure when the galaxy distribution demands it. This flexibility costs me precision on any one parameter, but it buys me truth. And truth in a field where everything luminous is riding an invisible scaffold is the only currency that spends across methods. Because the future catalogue will live or die by speed and rigor together, I think hard about automation that doesn't anesthetize judgment. Shape measurement pipelines need to carry their own self-calibration, which means injecting artificial galaxies with known sizes and ellipticities into real images on the fly, letting the code measure them and learning the biases. Contextually, faint objects in crowded regions are measured differently from bright objects in clean fields. Photometric redshift codes must produce not a single distance, but a full curve of possibilities for each source. The lensing inversion then weights each background galaxy by the appropriate lever arm according to that curve. Spectroscopic targeting must be greedy in the right places, use a coarse spine to find the segments with the largest curvature uncertainty or the largest density ambiguity, and spend the next mask there. I like to say spend error where it pays down error, because it forces me to ask where the next hour on a telescope moves the posterior the most. Let me talk like a hydrologist again, but this time with a meter stick. If I define the axis along the spine as S, with S increasing toward the cluster, and I define R as the shortest distance from the spine, then any property of galaxies or gas becomes a function FSR. Star formation rates, quenched fractions, gas phase metallicities, AGN incidence, disk to bulge ratios, radio, jet luminosities, even subtle indices like the 4000 angstrom break that age stellar populations, all of them plotted in these coordinates sharpen. In ordinary sky coordinates, curvature smears out gradients. In spine coordinates, the gradients line up with their causes. If the quenched fraction rises sharply when R drops below a fixed value, regardless of S, I am seeing a radial threshold set by ram pressure or tidal stirring. If metallicity climbs steadily with S as I approach the node, I am watching a long marinade. If AGN activity peaks at some characteristic S before the splashback radius, I am seeing a trigger zone where fresh gas and rising ambient pressure meet. None of that requires beautiful images, it requires honest coordinates. I don't want to dodge the small physics that can creep into big maps. Dust in the Milky Way can redden background galaxies and bias photometric redshifts. I need all-sky dust maps calibrated against stellar color standards to correct the colors before lensing ever sees them. Atmospheric dispersion can tilt spectra and degrade redshift precision if I take data at high air mass. I need to record the hour angle and parallactic angle for every exposure and fold those into the pipeline. Even tiny thermal drifts in a spectrograph can shift lines by fractions of a pixel. I need arc lamp frames before and after each mask, and a comb or skyline model to track residuals. It sounds fussy because it is, and it is fussy because turning a whisper of shape distortion and a millimetre of spectral shift into a map of 1 billion trillion suns worth of mass demands that fuss. I say that aloud to students demand the fuss, because the romance of the cosmic web rests on a pedestal built from mundane care. I lean back and consider the network page. Once I have a half dozen spines around different clusters, I can ask questions that don't make sense for a single field. For instance, do clusters with faster current mass growth, as measured by the anisotropy of their splashback radii, exhibit thicker filaments on average? If yes, lane thickness is a contemporaneous barometer of node appetite. Or is the curvature of lanes larger in supercluster environments where neighbouring mass concentrations torque the network more strongly? If yes, bends are not merely aesthetic, they are fingerprints of the wider landscape. Or at fixed cluster mass, do lanes with more infalling groups deliver satellites with higher quench fractions, a sign of pre-processing upstream? If yes, the road's traffic mix matters. Those are not philosophy questions, they are database queries once the map exists. I should explain one more piece of mathematics in words, because it anchors so many of the numerical statements we make without thinking. The critical surface density that sets the scale between measured shear and inferred mass depends only on distances observer to lens, observer to source, lens to source, and on constants of nature, like the speed of light and Newton's constant. When the source is far behind the lens, the lever arm is long and the critical density is small. A little mass makes a noticeable shear. When the source is not much farther than the lens, the lever arm is short and the critical density is large. You need more mass to get the same shear. This is why deep imaging that pushes the shape catalogue to higher redshift pays off quadratically. Each new distant galaxy is both a new arrow in the statistical quiver and a longer lever. Longer levers move heavy doors. I also want to bring in a messenger we've barely met in this story: gravitational waves. Not because filaments themselves radiate in any detectable way, but because binary black hole mergers localized to galaxies riding lanes can in principle serve as standard sirens, distance indicators, whose distances are measured by the waveforms themselves. If a standard siren event lands in a galaxy whose redshift we know, and whose position in spine coordinates we can place, it adds a dot to the cosmic expansion plot with an environmental tag. Over time, with many events, we could ask whether the Hubble-Lemaitre expansion we infer differs subtly for galaxies on lanes versus those in the field, a far-fetched but testable way to look for environmental systematics in distance. Ladders. Far-fetched is allowed when the apparatus is honest. The data will say yes or no. I owe attention to the neutrino page again because the patience of this problem is inspiring. Neutrinos wash out power on small scales in a way that leaves filaments slightly smoother. But slightly is the operative word. The way forward is not to expect one lane to shout the answer. It is to measure thickness distributions for a population of lanes at several redshifts and to compare them to forward-modelled mock universes that include neutrinos at various masses. You let the mocks inherit your selection function, the same lensing noise, the same spectroscopic incompleteness, the same spine-finding algorithm, and you ask which neutrino masses most often produce a population that looks like yours. It's not glamorous. It is the kind of statistical accretion that mirrors the physics we study. Small contributions added patiently produce structure. Because I've been celebrating lanes as rulers, I should sketch how they interleave with other rulers without stepping on toes. Baryon acoustic oscillations give us a standard length scale imprinted in the early universe. Supernovae supply a calibrated brightness ladder. Strong lensing time delays measure distances through geometry. Filaments, if standardized, would be a weak ruler, weak in precision per object, strong in independence of systematics, and strong in complementarity because they live squarely in the late-time growth sector. If I can show that median overdensity within some fixed physical radius r times correlates tightly with cluster mass and redshift across the population, and if I can measure that median robustly with weak lensing plus magnification, then r times becomes a distance-sensitive observable. I would never replace the classic tools. I would add a new orthogonal handle. In cosmology, orthogonal handles are a hedge against elegant mistakes. I tighten the spiral back to galaxies, because that is where eyes go always. If small disks far out on the lane tend to align their spins with the spine, and if larger disks closer in tend to tilt perpendicular. What about the shapes of their dark halos, lensing around individual galaxies? Galaxy-galaxy lensing can measure average halo ellipticities when you stack many lenses and read the tangential shear patterns asymmetry. Place those measurements in spine coordinates and ask whether halos are more elongated along or across the lane, and whether that anisotropy flips where the spin flips. If the answers line up, then the whole talk story is not just artful language, it is writ in gravity's ink. I will not let magnetic fields slip away as a footnote, because they are the quiet carpenters of conduction and confinement. A lane threaded by ordered fields carries heat preferentially along itself, which could smooth temperature gradients that would otherwise form perpendicular to the spine. It also guides cosmic rays, which though sparse carry pressure and can affect how gas cools. A practical test is to stack Faraday rotation measures of background radio sources as a function of R and S. If the rotation increases toward the midline and flip sign across it, that's the telltale wrap. Combine that with the thermal Sunyaev-Zeldovich pressure map and with X-ray limits, and you can set joint constraints on electron density and magnetic field strength that neither messenger can set alone. Joint constraints are the future's signature. They are also the antidote to overconfident single probe claims. There's a page titled Void Etiquette, and it makes me smile because it is half joke, half instruction. If a lane grows fat, the adjacent void must thin. If a node gorges nearby, lanes must show the scars. The etiquette is gravity's way of keeping accounts. I can measure it by defining voids with the same care I define spines, curvilinear coordinates around low-density centers, and cross-correlating their shapes and sizes with the properties of neighboring lanes. Does a void's expansion rate, inferred from galaxy ages, and number densities track the mass flux measured on the nearest road? If yes, then we can finally write in a single sentence that the health of the countryside knows about the width of the highway. If no, then either our definitions are sloppy or some other physics is moderating the conversation. Definitions matter, so do sentences we can defend. I close the notebook and return to the sky, because all of this only matters if the measurements land. I picture a Roman-wide field with clean shear maps, Euclid adding a second independent space-based set of shapes, ground-based imaging in the optical and near-infrared supplying colours for photometric redshifts, JWST, punching holes with exquisite depth where rare background sources turn the lever arm from long to longer. I picture 30-metre class telescopes laying down redshifts like stitches along the ridges, with hundreds of spectra per mask, each night tightening curvature and velocity estimates. I picture radio arrays pinpricking fast radio bursts by the thousands and handing us dispersion measures that we can stack against an ever-growing road atlas. I picture CMB experiments refining pressure maps until filaments glow faintly but routinely in the microwave. Routine is not a pejorative. Routine is the highest compliment a frontier can earn. So where am I truly at the end of this long walk with a dark ribbon that is no longer an allegory but an object, with coordinates that make physics legible instead of convenient, with cross-checks that turn systematics into new science, with a plan that spends precision where it pays down uncertainty, with rulers that will never be royal but will be sturdy, with a sense that neutrinos, magnetic fields and black holes are not add-ons but co-authors of the lane's biography. And I keep softly the same small refrain that has followed me from the first map to the imagined atlas, still assembling, because the road is still feeding its city, the city is still throwing tides back down the road. Our catalogues are still growing their limbs, and our methods are still learning their native tongue. Still assembling. In that repetition, there is no mysticism, only patience. The patience to turn faint stretches and tiny spectral shifts into bridges that carry mass heat metals and memory. And to read those bridges like an engineer reads a blueprint, like a naturalist reads a river, like a scientist reads a universe that writes its most important sentences in gravity's careful hand. I want to bring the discussion all the way down to the level of the likelihoods I actually write when I stop talking and start measuring, because that's where conviction comes from in a field built on faint signals. When I say we invert shapes into mass, the quiet truth is that I write a probability for the observed ellipticities of galaxies given an underlying shear field and a model for the instrument. And then I ask which shear field makes those probability is highest when multiplied together across thousands of sources. In words, each galaxy's shape is a noisy compass needle. The true shear wants to nudge the needle tangential to mass ridges. The instrument wants to smear it along its own preferred direction. The galaxy's intrinsic shape wants to wander randomly. I describe the intrinsic wander with a broad, nearly circular distribution, the shape noise. I describe the instrument with a point spread model learned from stars. I describe the shear with a smooth field whose gradients are linked to a convergence map, the projected surface mass density, by a set of differential relations that are elegant to write. And easy to say plainly, the shear is just the way that mass map slopes look from two perpendicular directions. The inference then becomes a balancing act. If the model adds too much shear, the likelihood falls because galaxies look overstretched, add too little, and the tiny coherences in their orientations go unexplained. Somewhere in between sits the ridge that wins. I keep a parallel track for magnification because shapes alone leave the mass sheet degeneracy unfixed. Magnification is conceptually simple, even if practically cruel. A heavier lens makes background galaxies a little bigger and a little brighter. As a result, at a fixed detection threshold, you gain some galaxies that were just too small or too faint before, and you lose some that were just large enough or just bright enough to count without the lens. The overall number density shifts depending on the slope of the counts versus brightness and size. In a field dominated by a filament, those count changes are not round. They trace the ridge. I fold that into my likelihood as an extra term that says in words, galaxy surface density should be a hair higher along the bridge than alongside by just the amount dictated by the geometry and the count slope. It's not as clean as shapes, galaxy clustering and selection effects tug at the same numbers, but when shear and magnification agree on where the ridge lies and by how much it weighs my shoulders relax, I don't want to bury the step where projection becomes depth, so I talk to myself like a teacher. A two-dimensional mass map is a shadow. To lift the shadow into a three-dimensional arch, I need distances. Distances in practice are redshifts. Spectroscopy gives me spikes, precise positions in depth for bright enough galaxies. Photometric redshifts give me clouds probability curves for fainter galaxies based on their colours. I lay a curving parametric path through the sky, my best guess for the spine on the plane of the sky from the mass map. And I ask the spectroscopic galaxies which of them want to sit on that path in 3 dimensions. The ones that cluster tightly around a continuous, sinuous trend in redshift position space become my beads. Fitting that trend with a smooth curve in space gives me the 3-dimensional spine. Around that spine I define a thin tube in depth and a widening tube in the plane to gather likely members while cutting away interlopers. Every step of that selection is audited by null tests. I can recite, reflect the tube across the cluster and the membership should vanish. Shift it off the ridge and the coherence in redshift should collapse. Scramble redshifts within their measurement uncertainties and the spine should persist only within the allowed wiggle room. If it survives, the lane breathes as a single object in 3 dimensions rather than a superposition of coincidences. I want to be honest about how I turn galaxy redshifts into flows without fooling myself with the Hubble wind. Every observed redshift mixes 2 motions, the smooth recession from cosmic expansion and the little extra due to local gravity. I subtract the smooth piece by evaluating the expansion rate at the filament's redshift under a fiducial cosmology. Then I average the residuals in bins along the spine, mindful that virial motions inside small groups can puff up the scatter and bias the mean if I'm careless. The safe practice is to downweight galaxies with large group membership, or to model the group orbits explicitly by first identifying substructures along the spine. When I've done that, the mean residual along the lane becomes the infall profile. It rises from near zero far out to a few hundred kilometers per second closer in peaking as the node's pull stiffens. The shape of that profile is a quiet ruler too steep, and I've likely over-subtracted the Hubble flow or mismodeled distances. Too shallow, and my mass map is probably underestimating surface density because my shape calibration is conservative. Flow and mass must agree. Flow and mass must agree. I hold that line in my head because cross-consistency is how a result graduates from persuasive to reliable. I also put serious weight on something that sounds like alphabet soup until you see its power, the decomposition of the shear field into E and B modes. Gravity to first order makes only E curl-free patterns. If my mass inversion yields a strong B pattern along the ridge, I don't congratulate myself on a mysterious new physics. I fix my pipeline. B often means my point spread model left a directional scar, or my coad of dithered images built a tiny anisotropy into the pixels. All my photometric redshifts have color-dependent systematics that translate into geometry mistakes. I run the inversion on rotated galaxy shapes, turn every ellipse by 45 degrees, and the E should flip into B. If it doesn't, error lurks. I split the catalogue by galaxy size, by signal to noise, by where on the detector they landed by observing night. The ridge should persist with the same amplitude within the honest error bars. When it does, I let myself proceed to poetry. Until then, I stay in prose. Because nothing in the sky is a perfect cylinder, I give the filament's cross-section the freedom it deserves. I allow an elliptical core. I allow a mild twist with arc length so the central axis can wander a little. I allow for braiding by admitting two near-parallel ribs if the galaxy distribution demands it tied together by a prior that prefers one unless the data insist on two. These add parameters. Parameters add variance. Variance lowers raw significance. But significance divorced from truth is not a currency I spend. Better a slightly broader error bar for a model that admits the filament's personality than a thin error bar wrapped around a fiction of symmetry. I keep a separate page labelled electrons because the most satisfying close of a budget is the one that counts the baryons we are supposed to have. Fast radio bursts turn into accountants in this story. Each burst's dispersion measure adds up the number of free electrons along its path, a modest excess in dispersion for sightlines that pierce the lane compared to those that don't, when averaged over many events, is exactly the kind of gentle, cumulative signal that convinces me I am weighing the warm-hot medium rather than dreaming it. I stack dispersion measures as a function of distance from the spine in the same SR coordinates I use for galaxy. If the curve rises monotonically toward r equals 0 and roughly follows what a cylinder of ionized gas would produce, the inference tightens that the lane contains the hidden baryons in roughly the fraction we need. If the rise, stalls or wiggles substructure and temperature phases are at play, I cross-check with the thermal Sunyaev-Zeldovich imprint pressure, mapped by the way hot electrons nudge ancient microwave photons up in energy. When dispersion and pressure agree in shape but differ modestly in amplitude, the difference tells me about temperature. It sounds nearly miraculous to get temperature from a difference of maps. In truth, it is just dimensional analysis in careful coordinates. I refuse to let magnetic fields remain a whisper because Faraday rotation is a letter-perfect test once the geometry is known. Polarized radio sources behind the lane are precious. Their polarization angles twist by an amount proportional to the integral along the path of electron density times the magnetic field component along the line of sight. If field lines wrap the filament, the line of sight component flips on opposite sides of the spine, and the rotation sign should flip too when I move from R positive to R negative across the midline. The signal for any one source is tiny, stacked across many aligned in SR and corrected for the Milky Way's own foreground twist. The flip is a geometric signature no other nuisance can fake easily. When I see even a hint of that pattern, the lane stops being only gravity's creature. It gains a magnetic biography. I also want to address the question that never quite leaves the room. Could modified gravity without a massive dark component do this? It is a fair check, and it pushes me to clarity. In plain terms, any alternative must let the same potential that bends light by exactly the measured amount also accelerate galaxies by exactly the measured infall, and also reproduce cluster-scale strong lensing when present. Also behave like general relativity in the regimes where it has been tested to death. Some theories can bend one or two of those beams, but not all at once. A 3D filament raises the bar because it correlates the lensing map with the velocity field along a particular curved path. The gradients of the same scalar field must explain both, and the path's curvature and the node's depth leave little room to hide. I do not declare closure, I do declare a clean arena for the alternatives to play on. I keep my engineer's hat on for one more practical knot, the way survey choices ripple into inferences. If I select spectroscopic targets by brightness alone, I bias toward massive quenched galaxies that may avoid the very gas-rich outskirts I care about. If I select by colour, I may over-represent star formers, whose emission lines are easy to measure, but whose dynamics are puffed up by winds. The cure is an iterative targeting strategy. Start broad, identify the spine measure where the uncertainty in curvature and density is largest along S, and then fill those segments with a deliberately mixed cocktail of galaxy types waiting by the current samples in balance. It's not glamorous to think about target masks as levers on scientific risk, but I've learned that the most cosmically ambitious results are often constrained by the most human of logistics. I realise I have leaned heavily on the lane as a pipeline and as a ruler. I want to hold it in mind once as a pedagogy. I imagine a student standing at a whiteboard with a marker and no symbols. I ask them to explain in words why a background galaxy farther away gives a longer lever for lensing than one just behind the lens. They draw a triangle in the air and say because the path has more room to bend. I ask them why the B mode is a canary for systematic. They say because gravity's tidal stretching has no swirl, so swirl means we did something. I ask them why the magnification test helps fix absolute mass. They say because a heavier blanket doesn't only stretch shapes, it changes counts. I ask them why the dispersion of 1,000 fast radio bursts can weigh the invisible gas. They say because each tiny smear adds, and the road makes the adding coherent. When a map turns into sentences that a tired mind can keep afield is healthy. I bring it back to numbers because numbers anchor joy. A central overdensity, a few to 10 times the cosmic mean, within a cylinder, 1,000,000 light years in radius. An infill profile that peaks at a few hundred kilometers per second relative to the Hubble flow within tens of millions of light years from the node. A dispersion measure excess of a few tens of units for sightlines piercing the midline compared to off-lane sightlines consistent with a warm hot plasma at a few million degrees. A faint but consistent thermal pressure dip on microwave maps tracing the same curve. Hints of Faraday rotation, that flip sign across the spine when stacked. Spin alignments that favour disk axes parallel to the spine for small halos, but tilt toward perpendicular in larger halos with the flip mass creeping lower as I move closer to the node. Those are not epic numbers, they are the kind that accumulate into confidence. I think about scale for the last time before closing this art because the mind's eye needs calibration. 60 million light years is a measure of length and patience. Light covers it in 60 million years. Gas crosses it if unimpeded on timescales that stretch toward billions. A cluster at the node grows by a few percent of its mass per billion years by sipping along 2 or 3 such roads. The road is not a torrent, it is a river with a deep, steady pull. We caught one in 3 dimensions. We measured its thickness, its bend, its flow. We listened for its heat in the microwave background. We counted its electrons in radio whispers. We watched spins twist in its tides. We checked that our instruments spoke honestly by looking for swirls where gravity cannot draw them and by asking magnification to agree with shear. We let the model breathe enough to admit braids and kinks, and we asked simulations to humble themselves by wearing our data's imperfections before they dared compare. We wrote the result in sentences first and in code second, so we could keep both a poet's picture and an engineer's plan. So I end where I began, with a map I can hold in my head and a method I can hold in my hands. The dark scaffolding of the universe is not a rumour to me anymore, it is a measured road. Still assembling because matter has not stopped sliding, because clusters have not finished eating, because surveys are just now stretching their eyes, because our pipelines are still learning to calibrate themselves while they work. Still assembling, and underneath the refrain, there is the quiet satisfaction of a ledger that balances at last a bridge, tens of millions of light years long, weighed by the light. It bends traced by the flows. It guides warmed by the energy. It releases magnetized by the fields. It carries narrated by the spins. It twists and made legible by a discipline that turns whispers into maps. I want to land this journey the way I land a night's observing run, with a clean log, a clear sky in the mind, and a small set of sentences that would still be true if I had to defend them tomorrow with new data. The first sentence is steady. A dark bridge, tens of millions of light years long, has been mapped in 3 dimensions as it feeds a massive galaxy cluster. Its presence inferred not from light it emits, but from the way it bends counts and colours the light of others. Shapes of faint galaxies whisper a coherent shear that sketches the ridge. Magnification of those same galaxies adds a second signature that locks the absolute scale. Spectroscopy threads a spine through depth, turning a 2-dimensional shadow into an arched 3-dimensional road. Kinematics of galaxies riding the lane show a net drift toward the node, so mass and motion sing the same melody. Microwave background maps hint at pressure along the corridor. Radio bursts add up electrons. Polarization gradients promise wrapped magnetic fields. None of these messengers alone would compel belief. Together they leave me with that quiet, satisfying click of an idea turning into an object. I keep the second sentence just as plain. The measured properties of the bridge match what cold, nearly collisionless dark matter predicts for the skeleton of large-scale structure. The central overdensity sits a few to 10 times above the cosmic mean over million light-year radii. The cross-section is not razor-thin and not wall-flat. It is a softened profile steeper toward the center, tapering smoothly outward. The curvature is gentle traceable back to the larger gravitational landscape that tugs on the lane. The flow pattern rises toward the cluster peaking, where the gravitational well steepens and the splashback boundary sits closer to the center along the road than across it, just as anisotropic infall insists. Spin alignments of galaxies show the expected hints, small halos tending to keep their angular momentum along the spine, larger ones pivoting toward perpendicular as accretion geometry changes. These are not arbitrary anecdotes. They are the recurring motifs of a theory that begins with tiny, nearly Gaussian ripples and ends with sheets, filaments and nodes in the late universe. A theory that remains unromantic precisely because it keeps predicting the right kind of ordinary. I place the third sentence where an engineer would on craft. We made this map not by wishing for beauty, but by demanding discipline. Point spread functions were modeled from stars and audited to kill instrumental shears. Shape pipelines were trained with injected fake galaxies and forced to learn their own biases. Photometric redshifts were carried as full probability curves, so the lensing geometry could weight each source by the correct lever arm. Spectroscopic masks were laid with intent curvature first, ambiguity first, so the spine would stiffen where it was weakest. Shear fields were decomposed into E and B, and only the curl-free piece was allowed to carry physics, while the swirl was forced to confess systematic. Magnification was treated as the sibling. It is not a distant cousin, so counts and shapes could interrogate the same ridge from orthogonal angle. Null tests, rotated shapes, split samples, scrambled positions were treated as results, not chores. I repeat to myself, treat tests as results, because it is the habit that keeps wonder honest. I write a fourth sentence for energy and chemistry because the bridge is not a purely geometric toy. Matter falling down a gravitational gradient has to pay its energy bills. Some of that payment is heat at shocks, where counterflows meet. Some is turbulence that decays. Some is pressure that leaves its fingerprint on ancient microwave light. Some is magnetism amplified by stretch and fold. The warm-hot intergalactic medium, the hiding place of many of the universe's missing ordinary baryons, threads these lanes. It is hot enough to be tenuous in X-rays, yet plentiful enough to raise fast radio burst dispersions by a few honest tens when sightlines pierce the midline. Metals leak into it in drizzles and spikes from galaxies and groups. Dust survives for a while, then sputters. Magnetic fields reach nanogauss to microgauss levels that align polarization and steer cosmic rays. A spine in the right coordinates turns those subtle signatures from curiosities into a ledger. Count, cross-check, close the budget. Close the budget, I tell myself softly, because closure is not glamour, it is groundwork. I keep a fifth sentence for biography, because galaxies are the beads that make the string visible, and their lives are written in the lane's grammar. Far from the node, small disks live on smoother diets, their star formation rates less scattered if the cold supply is steady, more ragged if the inflow is clumpy and episodic. Nearer in ram pressure and tides raise the quenched fraction, bars thicken, kinematics warm. Infalling groups arrive like braided rafts, pre-processing their satellites in advance and leaving kinks chemical and dynamical in the sequence along the spine. If I bin everything in the road's own coordinates, FSR, where S is arc length to the node and R is distance from the midline, these trends sharpen from hunches into curves. If they persist across lanes and epochs, ecology becomes a function of infrastructure. Deliver first, shape later, deliver and shape deliver, and shape two verbs that once seen in data are hard to unsee. I write a sixth sentence to squarely face alternatives because the question belongs in the room. Could gravity modified in the right way with little to no particle dark matter draw an equally convincing map? Any contender must bend photons and pull galaxies with the same potential along a curved three-dimensional path whose mass and motion are now both measured. It must also leave strong lensing arcs and time delays intact in the regimes where they are cleanest, and it must avoid unmaking the exquisite success of general relativity in the solar system and binary pulsars. Some clever constructs step a distance down this path. A measured lane steps forward with both lensing and kinematics aligned, and the step is long. I won't declare the debate closed. I will say the arena is now fenced with geometry and flow in a way that makes hand-waving hard and post-hoc tuning obvious. I add a seventh sentence that glances toward rulers not because filaments will dethrone the classics, but because independence matters. If we can standardize a simple observable, say the median overdensity within a fixed physical radius at a given redshift, and show that it correlates tightly with cluster mass and evolves in a way consistent with growth of structure predictions, then roads can become weak rulers. Weak is not pejorative. Weak means each is noisy, but the ensemble is frank. When combined with baryon acoustic oscillations, supernova distances, strong lensing time delays and cosmic microwave background lensing, a population of measured lanes becomes an orthogonal handle on the same cosmic parameters. Orthogonal handles are how you avoid being fooled when one beautiful method carries a hidden global bias. I keep an 8th sentence for the near future's ledger because the tools are already warming up in their cradles. Space telescopes mapping weak lensing across enormous fields with stable optics will multiply the number of candidate ridges. Infrared eyes will push the shape catalogue to fainter, more distant sources, lengthening the lensing lever arm. 30-meter mirrors will lay redshifts like stitches along many spines, firming curvature and velocity field. Radio arrays will localize fast radio bursts by the thousands each year, turning dispersion stacks from hints into profile. Microwave experiments will sharpen pressure maps until lanes glow faintly but reliably. These are not speculations, they are scheduled instruments with teams and timelines. The essential work, the boring, beautiful work, will be to bind their products into one coordinate frame per lane and one common set of null tests per catalogue. Make boring things beautiful, I remind myself, because databases and checklists are the scaffolding of discoveries that look effortless in hindsight. I reserve a 9th sentence for humility because every map's edges are drawn with error bars. The absolute mass scale still leans on calibrations that can drift if colour-based redshifts are biased. Intrinsic alignments can leak into shear if redshift cuts are sloppy. Projection by unrelated structures along the line of sight can inflate or dilute a ridge if the field of view is stingy. Spectroscopic samples can over-represent galaxy types that are easy to observe and under-represent those that carry the dynamics we need. The remedies are unromantic and reliable. Rotate shapes for nulls, scramble positions split by size and signal to noise, vary the smoothing scales, reflect selection functions into mocks, require E without B. Demand that magnification, and shear agree within propagated uncertainties and pre-register analysis choices before turning the final crank. It sounds procedural because it is. Procedure is what lets the last plot of a long night sit quietly on the screen without my stomach clenching. I want a 10th sentence that speaks to why this matters beyond the pride of a solved puzzle. Maps like this change how I look at everything else. The Milky Way set on a minor road in a quiet basin reads as a beneficiary of modest infrastructure rather than as an isolated overachiever. Quiet environment buys time for a thin disk and a long gas-fed adolescence. A violent node on a major interchange buys drama and early quenching. Neither story is reducible to one lane, but the availability of lanes as measurable, comparable objects turns those narratives from metaphors into hypotheses. Hypotheses are testable. Testable means we can be wrong. Being wrong means we can learn in public, which is the only kind of learning that accumulates for a field. I leave an 11th sentence for education because clarity is a renewable resource. When I can explain to a first-year student why a background source twice as distant as the lens gives roughly twice the lever arm for lensing, I have made geometry sing. When I can point to a clean B-mode map and say that's the part we do not trust, I have made honesty visible. When I can narrate how a dispersion measure excess of a few tens translates into a column of electrons and then into a temperature via comparison to a small pressure dip in microwave maps, I have made dimensional analysis feel like alchemy that keeps both feet on the ground. When I can show spin flips with mass laid against the spine's coordinate, I have turned a musty phrase tidal torque theory into a plot with real points and real scatter. Those moments are not noise around research, they are the engine of continuity between generations. I write a 12th sentence as a promise to myself because promises to ourselves are how we keep tone aligned with method. Spend precision where it pays down uncertainty. Borrow strength across messengers without letting anyone carry a claim alone. Add lanes to the atlas even when they look ordinary because populations reveal truths that jewels can hide. Publish the nulls and the almost, other people's almost are often the seeds of your at last. Treat simulation outputs with the same contempt as real data. Blur them, bias them, undersample them before you compare fingerprints. Keep the coordinate system that respects the object, not the plotting software. These are small vows, they compound. And now I want a final sentence that holds both the grandeur and the accounting in one breath. We mapped a road of gravity 60 million light years long, weighed it with the light it bends, traced it in depth with the redshifts of its riders, timed its traffic by their residual motions, felt its warmth in the pressure it imprints. On ancient radiation, counted the electrons that lace it with radio whispers, glimpsed the twist of fields that wrap it, and found in the tally the ordinary miracle that a universe whose bones are dark can nevertheless be read by patient creatures armed with triangle spectra and statistics. Still assembling, because the road is still feeding its city, because the city is still pushing tides back up the road, because our catalogues are still gaining pages, because our instruments are still learning to see fainter, sharper, truer, because our hypotheses are still learning to earn their keep. Still assembling, yes, and I'm content with that. Not because incompletion is romantic, but because the act of assembling, the turning of whispers into maps and maps into measurements, and measurements into sentences sturdy enough to carry into tomorrow, is the point. I close the notebook on that thought, not to shut the story, but to keep it safe for the next page. I'll leave it here with one clean thought I can stand behind. Tomorrow we turn faint, coherent stretches of distant galaxies into a waggable map of a dark bridge, then lifted that shadow into 3 dimensions with redshifts and checked its depth with the way galaxies drift along it. Pressure in the microwave background, electrons counted by fast radio bursts and hints of wrapped magnetic fields, all lined up with the same spine. So the invisible became legible without asking for magic, only for geometry patience and discipline null tests. That is enough for me. If you want to open the notebook again, we can turn this single road into an atlas. But for now, I'm content to say we saw the universe's scaffolding where it stands, measured what we could, admitted what we couldn't, and kept the refrain that has guided the whole journey, still assembling.